Everybody. Good morning. My name is Igor Gaponov. I'm a professor at Robotics University. I'll be chairing this session. Do we have all the speakers here? So let me quickly check if we have everybody here. So Kirill Artyomov, I can see you're sharing the screen. Is everything okay? Can you unmute yourself?
Yes, I'm ready.
Okay, please wait a second when I make a call out. Then Sergey Savin, he told that he'll be there shortly. Mikhail Kakanov from the 10:30 talk. Okay, probably not here yet. Then anyone from the 10:45 talk on gain selection of active damping? Igor Shardyka, Igor Dalev, Vladislav Kopolov, and Viktor Titov. Anyone from this group, from the RTC? Do we have any speakers from there yet? Okay, I guess not. Hopefully they will join. Okay then, let's start the session. Welcome everybody. Today is the first day of the NEAR 2020 conference. Unfortunately, we have to do it in the online format, but such is life. So let me welcome our first speaker, Kirill Artyomov from ITMO University, talking about a two-stage motion control system. So please go ahead and continue with your presentation.
Oh, thank you. My name is Kirill Artyomov. I present the work on the topic design and validation of two-stage motion control system for by-air quantum key distribution. Nowadays, we can see that our cities and the roads between them are getting smarter. Hence, all objects begin to be able to communicate with each other through various communication channels. The picture on the slide shows how it might look. In accordance with the papers in field of information security, there are critical problems in the securing communication channels in complex networks. The main problem with this is how to transfer encryption key to another agent so that this key does not intercepted by the hackers. The reliability of modern encryption algorithms relies only on the complexity of mathematical problems. An alternative approach is to use quantum cryptography or quantum key distribution. The main idea of quantum key distribution is to transmit information between two nodes by sending single photons following the special protocols. Due to the use of the Heisenberg uncertainty principle in quantum cryptography, it is impossible to intercept the encryption key without finding itself. Now, quantum key distribution by air is actively developing, where an optical receiver and transmitter are used. Due to the too weak transmission signal associated with the transmission of single photons, it is required to ensure high positioning accuracy of telescopes. The figure 3 shows two optical telescopes, transmitter and receiver. The transmitter is rigidly fixed. The challenge is to position the floating receiver to ensure high alignment accuracy. In other words, it's required to align the optical axis of the telescopes. The figure 4 shows how to solve the challenge using video camera. Accordingly, due to the fact that the aperture of the telescopes is relatively small, it's necessary to ensure high accuracy of the receiver positioning. The telescope can be installed on the, for example, robot manipulator, but then it will be an additional load that will decrease the accuracy positioning. In this way, two-stage alignment system was proposed. For the pre-alignment stage robot manipulator with the eye-in-hand robot with the eye-in-hand camera can be used. For fine positioning state, last two links or precise pan-tilt platform can be used. At the second stage, the feedback is The feedback is power of signal from a quantum key distribution system. Let's start with the pre-alignment stage. The robot model is given by equation 1. The overall control system on the stage is illustrated on the figure 5. This shows that all measurements are presented in discrete time, and the control goal is set in the camera image space. The control goal is defined as in equation 2, whereas E is error and P is current position in image space in pixels, and PD is desired position of visual marker fixed on the transmitter in image space 2. The classical image-based visual surveying algorithm is given by equation 3, where the lambda is function and its value decreases when approaching the control goal. Next, we implement 4 different controllers. The first is just PD plus gravity. In this case, we use nominal parameters. The second is PD plus gravity, but parameters of gravity vector was estimated. To estimate the parameters of gravity vector, it was written in regression form. Further, the optimal configurations were obtained. Using these optimal configurations, partial identification of dynamics of the robot manipulator was performed, and finally least squares method was used. For comparison, a classical computer torque controller was implemented, which is defined in equation 9. The last implemented controller is a time delay controller. It is not necessary for the controller to know the overall dynamics of the system. Based on the assumption that the dynamics of robot manipulator is much slower than the sample time, it is possible to extract the dynamics from the previous step in control loop. The affine positioning system in the work is presented by 2 heuristic algorithms for finding a minimum without knowing the gradient function. The main idea of the first algorithm that we call snake algorithm is to find the minimum of signal noise moving horizontally or vertically until the noise at the current step increases. Then the direction of movement changed by 90 degrees, and the algorithm continues to work until it reaches the specified noise threshold. And the second algorithm, circle, is to find the minimum of signal noise moving by a circle. As soon as the minimum is found, the size of circle decreases and its center shifts. As soon as and this continues until the minimum noise threshold in the signal is reached. Here is shown the transients for image-based visual surveying algorithm. On the figure 8 can be seen that PD plus gravity with estimation parameters controller is sufficient and has comparable performance. Here is shown transients for second, third, and fourth links in joint space. Finally, the 2-stage position system was presented. The validation of pre-alignment stage was performed. In future work, we will present simulation results for fine positioning stage and full experiment results for overall 2-stage positioning system will be presented. Thank you for your attention.
Thank you very much, Kirill, for your talk. I just wanted to reiterate one more time that for all those who are watching, please feel free to ask your questions in the chat, and we'll make sure to transfer them to the speaker. As of now, if you don't mind, I have a couple questions. So in the talk you've shared, so when you were discussing the computed torque control, can you please show this on the slide? So here, yeah, so you have kV times the error in velocity, if I understand correctly, correct? And so if you're planning to do experiments, how do you think you will measure the velocity?
It is estimation from maybe simple derivative, numerical derivative, or we can use some filter.
And so you think the accuracy will be enough to do this experimentally? The accuracy in you know, inertia metrics estimation and velocity estimation?
For this case, we use a nominal matrices because we performed this in simulation. So in real life, these matrices will be estimated from a full identification of dynamics.
Mm-hmm. And also, if you could show us again the transient responses that on slide maybe 12 of different controllers, when you compare the results of different controllers. Yeah, so that was very interesting, and it's just that you have in quite interesting overshoot in the computed torque graph inlet, right? I know that the magnitude is very small, but could you please comment on why you might have this overshoot, whereas all others don't produce this kind of behavior?
I think that this I think it is because gain matrix is too proportional part. Yeah, now how to say? A proportional part of PED controller in computed park, computed torque controllers is too large.
Because we would expect maybe one of the best performances here, right? If it's the model is correct and is done in simulation. It just was interesting to see. Yeah.
Yes, it depends from parameters of controllers.
I see. And since we don't have any other questions in the chat, maybe I can ask one last one. So for the time delay controller, right? In the picture, it looks like at first you was no, it was here. So you are starting. So in the top, in the bottom right picture, right? For the time delay controller, it looks like you are starting to move to the left first, and then converge towards the goal, right?
Mm-hmm.
And also on the plot on the left hand side, it looks like you are going the other way, right? Initially. So
Mm-hmm.
could you please comment on this and on the influence of time delay on this behavior?
I think this depends from initial values of controller, and on the first step of control loop, the torque for previous step is unknown.
Okay, I see. Thank you very much, Kirill. Yeah, so it seems like there are no other questions. So thank you for your talk. And I would like to ask the next speaker to prepare.
Mm-hmm. Okay.
Thank you. So the next paper will be by the group of Sergey Savin, Oleg Balakhnov, and Alexander Klimchuk of Innopolis University. Sergey, can we hear you?
Yeah, I hope you can.
Okay, yes, everything looks fine. So just one last time, for all the participants, please don't hesitate to write your questions in the chat, and we'll make sure to transfer them to the speakers. And so let's proceed. And Sergey, you have the floor.
Thank you so much. And it is a great honor to speak in front of such an audience. I'm feeling a little bit nervous, so I hope you will excuse me. Now, the topic I'm going to present to you is special because it is a new project for our team here at Innopolis University. It is a project about tensegrity robotics, where we study different aspects of controlling dynamics and shaping trajectories for tensegrity structures and robots based on them. This approach, so far this project produced a number of works, which are all of interest. And here, what I will try to do is, in this talk, is kind of guide us through a lot of them. And finally, we'll see the method, which in particular is highlighted in the paper. And it is so happens that the method derives from our previous work. So all of it will come naturally. Now, what is tensegrity? Tensegrity in general is a collection of rods and elastic cables. The rods are what experience compressive force, and cables is what experiences tensile forces. No other forces should be experienced by the elements, structural elements of a tensegrity structure. Tensegrity structure should also remain stable, and it should be able to remain stable under small perturbations without collapsing and losing its volume. As you can see on this picture, it looks kind of surreal, but if you saw them in real life, you would understand that. It works perfectly fine because of the tensile and compressive forces. Here, for the purpose of this talk, we'll consider one of the points of a tensegrity structure as an end effector. So we'll effectively say we want to control the position of this point. And we even have the trajectory in black here for this point, a desired trajectory. And we will say that some of the cables are actuated, meaning that there are motors that can actively change the arrest length of those cables. By arrest length, I mean the length which they would assume if no tensile forces are applied to them. So this kind of allows us to think of the structure as a very strange type of manipulator. This is mostly for semantic reasons because we have good terminology for manipulation, but not for any deep insights into differential equations or like dynamical models of those things. So please don't take too serious, like the comparison of terminology too seriously here. I will try to be as explicit as I can about it. All right, and those structures have a number of advantages. I'll just briefly mention one or two. They are very easy to transport. They're very difficult to break. They can be, generate a lot of stiffness for very low mass. And thus they are very applicable to explorations. For example, even for extraterrestrial exploration or for navigation through places where collisions are unavoidable. Let me give an example. So here we created a drone made that as a tensegrity structure. So this drone is basically a 6-bar tensegrity structure, and it can collide to the floor. Here it was on purpose. We made it just run to the floor, and it survives perfectly fine. And you can make it collide very hard indeed, and there is no damage because of the possibility of tensegrity structure to easily absorb impact based on the presence of all of those elastic elements on one hand, which absorb energy, and on the other hand, because all the forces in the structure are axial, so compression or tensile forces. And those are exactly the forces that the structural elements of tensegrity structure is good at withstanding. So that is the point of the structure, as illustrated here, for example. But let us go into our propositions. So first of all, before we can discuss what we did, just a quick reminder of how you model a basic tensegrity structure. Tensile forces can be modeled as equation 1 shows, simply as a force which is goes alongside a elastic element, and it is proportional to how much it is deformed. as shown here. And the proportional coefficient is given as a mu, for example. Static equilibrium can be obtained when all these forces acting on a single node. Nodes are here denoted as R. So when all of those forces for a single node are summed to 0, the node will be stable. When all of this sums to 0 over the whole structure is stable. That is one of the ways to describe it. You can also describe it in terms of rigid bodies, where you would have 6 equations per rigid body. Here is this simplification, but at the same time, a simplification that allows us to take into account elasticity of the rods. In any case, those equations provide you conditions for stability and a possibility to calculate elastic forces. Now, by the same way, you can calculate potential energy. There is a potential energy related to gravity and to elastic forces, or to potential energy stored in the elastic elements. The sum of those potential energies is a total of the system. And as you know, mechanical systems, especially ones without external forces, tend to assume position of minimal potential energy. That's true for tensor structures. After the motion is over, it assumes the minimal potential energy position for the given, for example, rest length of the cable. And that naturally provides you an algorithm how to calculate this position. So next, here is our most basic way to calculate the position of the tensor structure. Here we say that some of the rods have to, like Nij, some of those nodes have to remain a certain distance from one another. That will be a hard condition in case we assume our rods are not, in fact, deformable, those nodes. Or we can simply reject this condition and make everything deformable, and then we just minimize potential energy. Notice it is not a quadratic program, nor it is any sort of convex program. So it would be difficult to solve. It can potentially have local minima, and it is not solvable by convex optimization solvers. It can be solved using interior point methods, though, and that is one of the approaches that we pursued. Another one is local linearization. So let me move us forward. What we can do is, well, there are a number of ways you can approach it. One is to linearize the forces. That was proposed to one of our previous papers. Another one is to maintain the problem to be nonlinear, non-convex, as I showed on the previous slide. But then to attempt to linearize the inverse problem. Let me quickly show how it can be done here. So what you can do is you can obtain a position of a tensor structure solving the previous problem, and then you can perturb the problem by providing a slightly different rest length of the cables. What you get is a new stable position which corresponds to those new perturbed rest length. You do it a number of times, enough to have a linear model, linear relations between the perturbed Cartesian position of the node and perturbed rest length of the cable. That provides you a system of linear equations. They are affine, and you can simply calculate the matrix as shown in the equation 8, and the model will be of the form 7. So with this linear model, it is correct locally, but it is not correct globally. So what you can do is just get an iterative algorithm as shown here. And what you do is you generate this model locally, and then you descend. Then you generate a new model, and then you descend. That is, the way you descend is up to you. There are as many gradient-based method flavors as you want. But that is the point. You locally linearize the structure. Another approach is to directly try to solve it as a nonlinear program. And yet another way is to do it all with the machine learning. All of those were explored by us. And I believe most of them are in the papers which are not yet published, so I cannot reference them yet. But you can also explore it on your own, as the ideas is clear. you have a relation between one dataset and another dataset, or one quantity and another quantity written as explicit equations. The only question is how to solve it fast. So algorithm here is, for example, iterative, so you can provide your own conditions for stopping it, but it is not necessarily the fastest option. All right, so this is in our overview, very quick, about what we did with forward and inverse problems. The same can be done with stiffness. So we can do exactly the same approach with local linearizations, or with providing approximate models to solve forward and inverse stiffness problem. Here, though, we are going to a slightly different aspect of all of this situation with tensegrity forward and inverse problems. And that is, we want to try to find workspace of a tensegrity structure. And what we find very interesting here is that the workspace depends not only on the structure itself, not only on its configuration space, but also, and quite obviously, on the actuation pattern. Actuation pattern here means that not all the cables are actuated, as you would expect, because every actuation means a motor. Motor weighs a lot comparatively to the rest of the structure. So you wouldn't want to put a lot of motors in there, as you would want to put as few as possible. So here, the actuation pattern is shown by red cables. The 4 red cables in the front are cables that are actuated. And you can see that they're directly connected to the end effector. So here you would expect, maybe intuitively, that the workspace would be, at least maybe relatively well-defined, because you can directly move around this node compared to the other nodes. But you need to understand that the whole structure is moving. So it is not actually clear how the workspace would look like. But what if I tell you that instead of those 4 cables, I would actuate some other 4 cables, leaving those 4 unactuated? So in fact, there are no direct connections between the end effector and motors, only indirect ones via passive cables. In this case, how would the workspace change? Well, what we can do is just iteratively solve proposed problems. Is the first one or the second one? First one, forward kinematics, second one, inverse kinematics. As I said in the beginning, those terms come from manipulation theory on robot arms, but here they are applied to mean find node position based on rest length, or find rest length of the cables based on node positions. So you can solve either one of those, and to get a resulting workspace. If you solve forward kinematics, you need to iterate through all your cables, change their rest length in a, for example, grid fashion, and you would obtain a number of points which are obtained by your end effector. On the other hand, if you use inverse kinematics, you can just check which positions of the end effector are possible indeed for, and which are not, by solving inverse kinematics for each of them. Second one will have a more geometrically structured workspace in terms of points. There will be no overlap, for example. First approach will introduce overlap. So you can expect, for example, one point is reachable by 2 different types of change in rest length of the cables. So both are interesting. So let me present to you how workspace looks with this approach, with overlap. What we did is we changed the rest length of the cables in grid fashion. And then we get rid of the overlap by using an approximation of the surface. So what you see here is a sort of a polynomial approximation, piecewise polynomial approximation of the surface of the workspace. And you can see on the left workspace of directly actuated cable case. So the ones on the picture. And on the right, you can see what happens when none of the cables directly connected to the point are actuated. You can see the workspace became noticeably smaller. But in both cases, it has a distinct geometry, which in some ways suggests that you can generate workspaces in a large quantity And you can use those workspaces to make a decision about the connectivity pattern of your tensegrity structure. Especially if you can feed those into any kind of machine learning tool to automatically predict workspaces based on your changing pattern. We see this as a new instrument for designing tensegrity structures. However, there's still a lot of work to be done, especially in automating generation of those 3D shapes, and even more so in making a standard description of those workspaces based, as I mentioned previously in this talk, on which problem did we solve, inverse kinematics or forward kinematics, since one produces overlap and another does not. So a lot of work still to be done here, but we can see that it is perfectly possible to, with those simple tools I just presented to you in this talk, generate those workspaces for tensegrity structure. This is just for one point, but we can do the same for bodies or for a number of points. And that is it from me. I hope you have questions, and I hope you learned something from it.
Thank you very much, Sergey, for your talk. So we are still waiting for the questions from the audience, but if you don't mind, I have a couple of questions from me. So when you were, can you please go back one slide? So when you're talking about the workspaces, maybe I missed, but what was the range of contraction on the cables? Do you fully collapse them, or do you only contract them in a certain range?
So the exact ranges were mentioned in the paper. I cannot quote them from the top of my head, and I apologize. But of course, they were limited, because the idea of a full contraction is, it depends on the cable. Some cables, will actually start to break way before you be able to contract them completely. So in practice, I think usually you would expect a very small range of contraction for a cable. And I don't remember exactly the numbers used in the paper, but in practice, you would always want to put limits on that.
Okay, thank you very much. And just another quick question. So you did this analysis for a 6-bar structure, correct?
Yes.
So do you have any intuition on how scalable your method would be? Because you said obviously there will be local minima for solutions, and what if you scale up, or what if you add the bars? Did you do any analysis of other structures, and can you comment on the complexity overall?
Yeah, we did use so this workspace is generated using forward.
Unfortunately, Sergey seems to have some issues with connection, breaking up. Okay, I'm sure Sergey will be back. I would like to ask the next speakers to get ready. Hopefully you're here. So yeah, Mikhail, you're here. Please wait a little bit. Hopefully Sergey will come back, and I'll invite you next. Glad to see that you are here. Let's wait, give another minute. This is the pros and cons of having conferences online, right? It's easy to get many people involved, but obviously there are some technical issues that we can encounter on the way. Okay, Sergey is typing that, yeah, he had some problem.
Yeah.
Okay.
Sorry about that.
Yeah, can you please finish? Yeah, just briefly for the scalability, because you were interrupted, and then we'll move on.
Yeah, so just to finish, as I said, for structures that we encountered in practice, which includes something like artificial tensegrity arms and other bigger structures than what you usually see in modern tensegrity robotics, we didn't see any problem with computational efficiency of the method. However, we expect when we go into hundreds of elements, we would need something better. And something better is local linearization, etc., which is already being proposed for forward kinematics, or machine learning tools, which are excellent at scaling. However, they offload the computational expense into generation of data sets. Sorry for the trouble again.
Thank you very much, Sergey, for the interesting talk. Thank you. And yeah, let me invite the next speakers to share their screen. So we have here the paper presented by the group of Mikhail Kakanov, Oleg Borisov, and Anton Pyrkin from ITMO University, St. Petersburg, Russia. Okay, so it looks like you're ready. Please go ahead.
Okay. Good morning, everyone. My name is Mikhail Kakanov, and I'm going to tell about LMI-based design of output robust controller with static anti-wind-up. Oh, one moment. Okay. It is outline of my presentation, and you can see this my structure of my presentation in footline, and which help to navigate of my presentation. Okay, firstly, all real technical systems are constrained, and we need to keep this fact in mind when we design our controller. Because if our controller include internal term, when the signals goes beyond available limits, we can face to wind-up effects. This fact leads to increase overshoots, settling time of transitions, and we can lose stability of closed loop system in crucial case. Consider SISO plant with constrained input. In this case, we cannot measure state vector, and disturbance influence to our plant. We consider external disturbance as output of linear system, which is represented by equation 3, and with parameter rho and S matrix. The plant is minimum phase. It's the dynamic of our plant is stable. We know the relative degree of the plant, and we have parametric uncertainty. We know nominal parameters, but we has non-bounded parametric uncertainty. The vector of disturbance generator is known, and our control signal satisfies these conditions. That mean our input signal is saturated. The disturbance is bounded, and the nominal control signal can be compensate this disturbance. We consider we need to achieve two goals. Firstly, for unconstrained system, we need achieve global asymptotic stability, and when we consider input saturated input, we need to ensure semi-global asymptotic stability, and we want minimize L2 gain from disturbance to output variable. Control law confirms our saturation, and we choose nominal controller based on height gain approach. First equation, it is state observer. Next, it is observer feedback. Equation 7 represent control law with state feedback, internal term which compensate external disturbance, and anti-wind-up correction signal for compensate some negative effects which occurs when our control signal is saturated. Equation 8 represents internal model which compensate our disturbance. We need to choose observer parameters such as AQ, observer state matrix is Hurwitz, and feedback, observer feedback coefficients, it is coefficients of our arbitrary Hurwitz polynomial. Parameter of internal model we need chosen as choose as parameter G and gamma satisfy chosen relative to our generator, disturbance generator. Next, we write closed loop system, and when I tell about closed loop system, I use bold font for my parameter, and we can see that our vector B contains anti-wind up parameters. Consider the case without disturbance, parametric uncertainties, and take the anti-wind up coefficients equal to 0. We using this decentralized vector quadratic inequality for analyze saturated system, and we need get Lyapunov function for time derivative from the direction ax plus b var kappa, and we using new notation. Okay, I'm sorry. Condition on the slide indicates the existence of quadratic positive defined Lyapunov function. Next, we consider external case. We need let's return to case of presence of external disturbances. At this stage, we are interested two goals. Firstly, to ensure that the system is stable against external disturbances, and we need determine L2 gain from disturbance to the output variable. We rewrite condition which you can see above, and in this condition we need minimize parameter zeta. It is a minimum upper limit of L2 gain. Such as vector B contains our anti-wind up gains, we need introduce new variable for I'm sorry. We need a new variable theta for contain these gains. And this help us to avoid nonlinearity in matrix inequalities. And we achieve, we get this condition for closed system with anti-wind up and external disturbances. When we consider parametric uncertainties, we consider equation 18. It is ellipsoid, which center is nominal parameters. And taking into account this, we rewrite our condition, and we need to minimize x variable chi, new variable chi, absorb our parameter zeta with epsilon that help us to solving this LMI. So, consider numerical example. We consider linearized autopilot model for a surface vessel. This model widely used to analyze control problem for surface vessels when we need to stabilize our heading, and select model parameter as a parameter of fully loaded oil tanker, and rewrite this system to state space. On the slide, you can see simulation results, and we can see that in output signal, we achieved less overshots. Okay. Robust algorithm for controlling the outputs of the system is developed. In the presence of restriction on the input signals, undesirable effects of saturation of the input signal are compensated by a static anti-wind-up correction scheme. Approach to adjusting the coefficients of anti-wind-up correction based on the tools of linear metrics inequalities is proposed. And the efficiency of proposed approach is illustrated by example of autopilot system by surface vessels. That's all. Thank you for your attention.
Thank you very much, Mikhail, for your interesting talk. So if you don't mind, we're a little bit short of time, so I would like to ask the next group to prepare for their talk. And probably we still have time for just one short question. So you have showed that you did the verification of this model on an autopilot system, right? So
yes.
Can you please comment on the complexity of the model itself? So I see that probably this is the first order system, and how can you apply the method you propose with anti-wind-up for a more complex system, and for example, if you have multiple variables that have saturation in them?
Yes, we can use this approach for more complicated system, but it is we can use it only for linear system. For example, we can scale this model for dynamic position system of surface vessel. It's more complicated model, but for this work, I choose to illustrate this on the autopilot system.
Yeah, thank you. So I see it was an oil tanker model.
Yes.
Right. Okay. Thank you very much, Mikhail. Thank you. And I would like to ask the next speaker from the group of, so the next paper by the team of Igor Shardyka, Igor Dalyaev, Vladislav Kopylov, and Viktor Titov. Do we have any of the speakers in the chat? So the topic is on gain selection of active damping ejection controller for series elastic actuators. Do we have any of the presenters of that paper here in the chat? If not, hopefully they will join a little bit later. Then, if not, I would like to move on to the next speaker, who is Sergey Savin, if you're still here with us.
Of course.
Okay. Yeah, so can you please go ahead and present your paper?
Yes, 1 second. Let me share the screen. One moment. All right. Thank you again for having me. And no, hope this discussion, like the jump between topics, is not going to be overwhelming, and we'll still be able to, appreciate both of them. Now, in my previous talk, I talked about a completely new type of robotic structures. This talk is on one of the most traditional type of robotic structures, on walking robots. So, as you can imagine, walking robots have been around since forever, but the properties of walking robots are so diverse that they are still of great interest, and the number of challenges doesn't seem to go anywhere down. Now, this talk is in particular on one of the challenges, and that is contact interaction. We in robotics like model-based approaches, but model for contact is almost impossible to get. At least if you are planning to contact something that you didn't contact before, like a new type of surface. And when I say new, I mean just slightly new, something that is slightly different than before. Maybe even the robot itself is slightly different from before, like the parts that contact, like for example, shoes or feet surfaces changed through the life of the robot. For example, something stuck on them, like a small stone somewhere. And already contact interaction scenario is different. So here we are bringing us towards a different approach, which I'll hopefully be able to motivate. And that approach, just a heads up, is based on machine learning. We're going to have a predictor of normal reaction forces, and we're going to use it to implement our traditional model-based approach in control. All right, let's go ahead. So, as we said, we're talking about bipedal robots. You can see this robot has a very rigid body and very rigid feet. And it is very suitable for walking on a completely horizontal, flat surface. When you see videos of robots which walk on better surfaces, you often notice that it is either very impressive performance on flat surfaces or impressively possible performance on non-flat surfaces, but you don't see anything impressive on non-flat surfaces. That kind of represents where we are now as a community. We like to be able to predict contact, to have those good model-based approaches, such as jumping and running. Or if we cannot predict contact and we cannot use model-based approaches, we at least are capable of surviving and moving somewhat ahead. So here we'll try to move past that. Now, why do we want to bring machine learning tools for recognition of contact interaction scenarios? Well, first of all, as I said, contact interaction is difficult to model, especially when you don't know exactly how contact is going to look like. But second of all, it is very easy to measure things that occur within the robot. For example, reaction forces can often be measured directly by internal sensors, but even when you don't have them, which is often the case for most of the robots, they don't have reaction force sensors in the extremities, you can at least measure velocities, accelerations, etc. On the fly. And reaction forces, you can still measure them using external sensors, which is very easy to do. And in the laboratory, for those of you in the audience who are physically in the Innopolis University, you can go and see pressure sensors, which were built and experimented on R600. So it is very easy to measure those reaction forces in a lab environment. And you can get data set from that. And when you have a data set, you are just one step away from being able to implement machine learning strategy on something. And you offload a lot of computations and from the execution time to the training time. And you get stability of execution time. You know how long your algorithm is going to execute. And you have a clear way to improve in the execution, get more data. Of course, all of this doesn't answer all of the questions. For example, how do you collect data on the fly if you don't have a pressure sensor, etc. A lot of those questions are indeed open. But here we're trying to move one step at a time towards solving them. Now, one specific problem that we are solving in this paper is how to make this whole problem tractable. If you allow me to go back one slide and you look at how this robot is constructed, you will notice enormous amount of joints. The number of joints, especially on the fingers, is just staggering. And you probably don't want all this information in your data set. In fact, if you try to collect a huge data set, let's say 1 million lines, and you try to collect all velocities, all positions, and maybe other stuff, for example, actuation pattern, like, for example, what your actuators did, you will create enormous data set, which would require a big neural network, and it would just decrease the performance. And most of this information is not needed to predict normal reaction forces. So what we would like to do is to do feature extraction. So we would like to get the data and first compress it into something more concise and hopefully help training. So this is a particular problem that we are solving. But I would like to acknowledge that there are plenty of other problems that are still existing in the field that I mentioned just a minute ago. So sorry for not providing all the answers yet in this talk. I will just provide this one answer. All right, now let us move on. What is a walking robot? You can describe it with a very simple model, model number 1, which is well known in the literature. This model kind of assumes that your contact points cannot leave the ground, so like they cannot break the contact. That is incorrect. In fact, you would like to additionally add extra constraints on what reaction forces can be like. For example, you add friction cones. But as a general idea, equation number 1 works. And indeed, if equation number 1 is sufficient for you, you can hope to find reaction forces explicitly using equation number 2, which is proposed in one of the papers written less than a decade ago and is based on QR decomposition, the method in 2. So you decompose Jacobian of the constraints and you get exact model of your reaction forces, which doesn't take into account friction for limitations of friction, etc. So in theory, all of this works. In practice, of course, knowing the Jacobian of constraints kind of assumes that you know everything about contact interaction scenario, which you don't. But in simulation, you can easily use equations number 1 and 2 to get your data sets, which we do a lot because collecting data in simulation is simple and you can reject ideas based on simulation results very fast. But of course, you need to recognize that all of this is good for validation, but not for direct implementation of the robot, because for a robot, we don't have equation number 2. Instead, we have sensor data. All right. So this is how you just talk about the robots in a very brief terms. Now, how do we acquire data set? Well, first of all, as I said before, what we would like to capture is motion data. So we would like to capture positions of the joints. We would like to capture accelerations and control inputs. So, for example, what we can do is get a simulator and simulate the robot forward using some control law which was previously proposed to control this type of robot along some trajectories, which, for example, do not change contact interaction scenario if we want to learn one contact interaction scenario. We can collect the motion data. We make sure that the collected data represents the motion on which will be tested. In one of our previous papers, we report problems where the incorrectness of predictor was exactly based on difference in acceleration patterns between training and execution. And in our experiments, we collect data sets in the order of magnitudes of 200,000 elements. This is one example. In a different paper, we report doing the same thing for R600, so a full size humanoid robot. You can do it using MATLAB software that we developed, or you can do it using, for example, Drake developed by MIT. there are plenty of ways to collect reaction forces based on the model of the robot, but all of them are involving solving, finding dynamical expressions for example, joint space inertia metrics, etc. So, all right. Now, what we are proposing. We discussed a number of methods for making the dataset to extract features from the dataset. There are plenty of those approaches proposed in data science. And if you read through the paper, you'll find a number of them. But what we really like is feature extraction based on single value decomposition and autoencoders. I didn't bring a single value decomposition to the slide because it is quite famous. Basically, what I mean is more like principal component analysis, where you have a very robust and very simple way of rejecting some of the dimensions of the data and seeing how much of the explained variance remains. And that's it. You get very good results from that. And you can complement this with a linear regression to later tune your network. And you can even avoid the training proposed in normal DNNs. Or you can train a DNN after, like there are options. Here, what we are looking at is more of a machine learning style approach. We train an autoencoder, which has an intermediate middle layer, which is smaller dimensions than the input and output layers. But input and output should actually be the same. The encoder should predict its own input. That is a famous concept. That's what we use. And tuning the dimensions of the encoder and intermediate layers, we can tune the encoding of the data. And as we saw, sometimes reducing the dimensionality just by 2 actually significantly improves the behavior of the problem during training. So, however, it is not universal. So let me show you what we encountered in practice. This is MSE, mean squared error, for different structures of encoders. So you can see the encoders, some of them were had like dimensions even bigger than the dimension of the problem. Some of them had dimensions smaller than the dimension of the problem. I believe the dimension of the problem is 36. So what you get is a number of structures which perform kind of similarly. The big outtake for us for this was that you don't have to include a lot of layers. Just 2 layers was enough, but 1 layer wasn't enough. As you can see, the first 3 lines represent 1 layer encoders, and they didn't perform as well. 2 layers and 3 layers perform similarly. However, you need to choose the correct dimensions of those layers. This already represents a great reduction in terms of parameter tuning that we have to perform for each new network design, making it stay within 2 layers and tuning only 2 parameters, the number of neurons in the layer, makes it much, much simpler. And you can represent this whole thing as a 2-dimensional surface, which what accidentally was done in different paper by Eduard Zalev and co-authors. So you can hopefully see this paper already online, and you can see just how powerful it is. You can visualize completely the error based on the tuning of those just 2 parameters. And here what we demonstrate is you can make do with those 2 parameters. That is what we showed in the experiments. Those numbers here are just for particular experiments after different number of epochs, but they show trends. You can perform, and we did perform numbers of experiments to confirm it, and the results stay. So they are statistically significant as we feel. Now, next question after that is, but how does this accuracy of the predictor actually influences things? So I started by saying that we should use it in control. And then I kind of went into saying, how about we first, train the predictor, right, that we can use in control. So to train the predictor, as I said, we use autoencoders to encode it and to make the training faster. But at the end of the day, after we have encoded our data, we just need to train it. And that is the question of how much data we have and all other hyperparameters typical for dense neural networks. We eventually will train it. But we'll always have to stop somewhere. We will never have accuracy, which is absolute. We will always have limited accuracy. So next big question for us, I think, besides the point of how to make the accuracy higher, is how to identify that the accuracy is enough. So here we propose a very simple metric. We train our predictor to a certain degree of accuracy. Next, based on this predictor and based on the method proposed in the original paper on using reaction predictions in control, we solve inverse dynamics. We solve it by substituting prediction into reaction force expressions in the dynamics shown on the one of the first slides in this presentation. And then we simply try to solve for U. We get the incorrect solution, of course, because the predictor is incorrect. And how much predictor is incorrect? This, for example, can be identified by the mean of the predictor error. It can also be identified by the variance. Here we limit the discussion to the mean. And by the way, the variance is also discussed, but simply in a different part of the paper. So you can look in the paper in this conference and we'll see the discussion of other statistical parameters. All right, so mean. We choose a different mean for our predictor error, and we plug it into the algorithm, and we simply calculate what is the control error. So what is the difference between actual inverse dynamics, so actual solution which makes our current point on the state space trajectory into a node, so something that can be stabilized, and between what we got from predictor. And we plot it on the data after making 1 million experiments. That sounds excessive, but it was very easy to do. So we did 1 million experiments for each of those, and we plotted the distribution of the error. As you can see, the distribution looks very nice. It is a lopsided bell curve. You can see it has a long tail to the right, which is obviously it would have because it cannot be negative. And you can see that the whole distribution kind of becomes more flat, and you can expect a bigger variety the more the mean is. The different experiments were different in terms of position of the robot, etc. So as you can see, actually increasing the mean by as much as 5 Newton meters, which is a lot, increases the control error significantly by a number of, again, Newton meters. That would be the units here. But it is still possible to control the robot with it. You would have to use disturbance rejections if you want perfect control. But we did try to control the R600 in simulation with those noisy predictors, as you see on these experiments, and actually works. However, when I say actually works, it worked for our implementation. For implementation of a different person, it may not work. So the point that I'm trying to make with this slide is you can actually see what kind of nonsense you can expect from this control. So you can, instead of going through the whole rigmarole of training the neural network and finding out how bad it is, you can actually try to plug in one of those errors from this shape into your current control without any predictor. Just make it worse by plugging in disturbance from this distribution and see if your control can handle it. If it can, then you will be good to go with the reaction predictor. In our future work, we'll actually describe how to exactly combat this, especially static error. But here we at least present how you can make sure that it all works. Well, that is it from me. I hope I didn't take too much time, and thank you so much for listening. Hope you have questions.
Thank you very much, Sergey. So let me read one question from the chat. So when you talk about 1 million experiments, do you mean simulation? and how performance is influenced when you move from a model to the real robot.
Yeah, when I'm talking about 1 million experiments, of course, I mean simulation. I don't think it is possible to do anything meaningful in terms of millions in real world. Performance, well, here's the thing. One good answer that I can give is the following. Some of the experiments were performed in ROS using exact same control system as we used in R600. So the only difference between those two was that R600 is a physical robot, and we used Gazebo to replace it and simulate the output of the sensors. Everything else, including all the software that runs on actual robot, was run in simulation. Plus, we added additional computational load based on using Drake to every millisecond calculate joint space inertia matrix and local linearizations, I believe. And those require enormous amount of time, and they require absolutely no time in actual real life, where you don't have to collect model data to calculate some stuff for logging, etc. Like the controls that you're going to have, it does require things like that. So for example, we did try computer torque controller or LQR. Those would require you to calculate all those matrices in real life. So you would have exactly the same performance as we saw in experiments. However, if your control does not require them, if, for example, you use the joint bias PID, which is used in most cases with R600, you'd actually have better, better life in a real experiment in terms of computation compared to what we had in simulation. Hope this answers the question.
Thank you very much, Sergey. And yeah, I think we are out of time, so I would like to thank you for your talk. And just one last time, let me reiterate. So do we have the speakers from the paper entitled on gain selection of active damping injection controller for series elastic actuators from the RTC? Igor Shardyka, Igor Talev, Vladislav Kopolov, and Viktor Titov. So it seems like the authors are not with us because of this. And let me invite the next speaker. So Alexey Mishkov from Whitmore University, St. Petersburg, Russia, talking about motion tracking. Please go ahead with your presentation.
Yeah, thank you very much. I'm sorry in advance for my voice because I'm a little bit ill, so I hope you can hear me. Just a second. Okay. So good morning, dear colleagues. My name is Alexey Mishkov, and I would like to present you the results of our work on adaptive nonlinear tracking approach for motion tracking applications. Why is it important? Right now, the task of motion trajectory estimation and the object identification can be found in very large amount of various application fields, such as security for like silhouette identification and object tracking, educational purposes, the workplace simulation in VR and AR environments. It is also needed to implement the avatar of the person who is educating into these environments. And in robotics, for example, it's for computer vision systems for mobile platform navigations. As our main goal of this work was to propose and test an adaptive nonlinear trajectory estimation approach. And so we set a few tasks for us to do so. The first one was to acquire the object position coordinates by the means of computer vision system. Based on this received set of coordinates to estimate an object trajectory using our adaptive nonlinear trajectory estimation approach. And the last task was to estimate the results of this approach work, which was based on internal model. So to talk about the nonlinear signal tracking approach that we presented, it is better to start at the very first. So consider the plant that affected by constrained exogenous reference input as shown on this slide. And this can be presented for our application, which we choose to test it on. For nonlinear signal tracking, it can be modeled as shown here, in which omega-1 and omega-2 is the state variables. Theta 1, 2, and 3 are unknown parameters, and the function of this function f is known. The goal of this algorithm is to track nonlinear reference inputs built on, just a second, some minor problems. Reference input by applying a control law, which ensures error estimation error to 0. So based on previous work done by Pirkin and Isidori in the work of output regulation for robustly minimum phase multivariable nonlinear systems, the control law of this form could be applied to our signal. Where k is a design parameter, but elements f and gamma should be designed specifically for considered exogenous nonlinear system. Also, as was stated in the work, there were two assumptions that we should take into consideration: that the nominal control law in which vectors x and omega are not measurable, ensuring error that ensures the error convergence to 0. This control law is known. And the second assumption, that there is a form of external disturbance that states as from the projecting formulas. So to design the control law under the existence of this form, it is needed to define the variables of the vector as shown here. So the model of external disturbances could be represented as you can see here. And as can be seen from here, both vectors are mutually expressive, which indicates the existence of a special form that was stated in a work that I stated before. So based on those assumptions, there is a system of the form which have a representation like shown on this slide. However, the previously stated control for law is not feasible since it relies on vector omega, which is not available in the stated system. So in order to fix this problem, the control law was redesigned as shown here, which is the steady state could be reduced to this form. Since function theta also relies on unknown parameters, it is needed to replace it with the estimate, which we can, in which the estimate vector is represented as can be seen here. So in order to estimate this vector, we need to implement an adaptation law, which can be seen here. So basically, the whole approach can be pressed in this model, the model of the diagram of the control law is adaptive internal model. The internal model is represented on this slide, where unknown functions are also shown. Not the experimental part. In order to conduct an experiment, the test stand was assembled. It was consist of the robotic arm cell Mitsubishi RV. As the visual sources, we were using time of flight depth cameras with Ranger 4000, and as the objects that we were tracking, which trajectory we were tracking was used a shiny metal ball, which have distinct features in a view of a camera. Then the reference trajectory by which the manipulator was moving was built by using a random oscillator. This trajectory, it is not known for the system, so it was used for the sole purpose of conducting an experiment in known variables, so we can estimate an error of our algorithm. In order to detect the object position, as I stated previously, the metal ball had a distinctive feature. Since it had a reflective surface, the center of the ball was, so we had to use MATLAB morphological operations to create a tracking mask, and based on that mask, we were deriving the coordinates of the object center. Why we were using morphological operations? Because we didn't really care about the noise of received data set. In order to prove the robustness of our algorithm, we needed a noise data, basically. So In conclusion, I can say that the proposed algorithm was applied to the three-dimensional trajectory tracking task, as I stated in the beginning, and the tracking error for each coordinates were estimated. And as can be seen here from this graph, for the one of the axis, the transient responses of the estimation errors led to 0. Here on this slide, you can see how we conducted for each of the derived coordinates. So x, y, and z axis on x, y, and z axis. On the left is presented the reference signal. The middle graph shows how the error were converged to 0, and the last graph shows how the unknown parameter were estimated, and they also converged to 0 in order to establish ensure the robustness and work of the algorithm. Thank you for your attention. I'm ready for questions.
Thank you very much, Alexei, for your interesting talk. So if you mind, I would like to ask a couple of questions. So if you go back to the previous slide, please. So in your adaptive controller, did you have any goals on desired settling time, for example, for all the transient responses for tracking? Alexei?
I
think there is something with
we were trying to
connection.
Yeah, something with the connect. I'll try to fix it right now. Hold on a second. Several other applications. Is it better now? Can you hear me?
Yes, we can hear you.
Apparently not.
Yeah, we can.
Oh, okay. So the goal for the goal for the time was not like set in stone, but it was aimed to be as minor as possible, and so we reached the convergence time of like in basically here from the graphs you can see that how yeah, this should be a bit better. Sorry. Yeah, here. So you can see in 10 seconds it almost converged to 0. So the further work, of course, is on improvement of that internal model that we are presented in order to decrease it even more, the response time, and to apply it to different tasks such as links of manipulator itself to detect the movement of all the links and to try to, well, basically to improve the parameters. But even here in this application, it was shown that the transient response time is pretty fast to what it is.
And could you please comment on why, for example, for theta1 angle, you have a much longer settling time? And which angle was this in the robot?
This is no, it's not about angles. Right now we were measuring only like the coordinates, the x, y, and z. It's basically, as can be seen here, it was based on adaptive law that we're trying to adapt the internal model to the external disturbances. And of course, it's really depends from the graph, which it is derived from. For example, here on the x-axis, the object was moving in almost like oscillator state, and whereas on x-axis, it was basically around the same area. So the transient response time is much more much smaller than for example, here.
I see. And one last question. So did you try investigating how different values of gamma affect the transient responses for different coordinates?
Yeah, for example, here it was experimentally proven, I guess, and yeah. So here, like I showed previously, here The gamma was based on these parameters, the theta parameters, basically. And under different circumstances, yeah, it was slightly different, as can be seen here. Here is the parameter of thetas, how they were changing is shown. I mean, the convergence of them, and it was based solely on them. So it is adaptation law. It was working by itself, to be honest. So it's adapting by having an external disturbance, by acquiring more and more data, as can be seen here.
Okay, thank you very much, Alexei, for your
Yeah,
interesting talk. Thank
you.
you.
Thank you for your attention.
And I would like to invite the next speaker, Ribi Abraham Bobby of Innopolis University, to share his screen and make his presentation. Okay, please go ahead once you are ready.
Is everything fine?
Yes, we can hear you well.
Okay. Okay, thank you, and good morning to everyone. So I will be presenting on hand-eye calibration using a single image and robotic picking up using images lacking in contrast. So I work in Innopolis University. I'll start the presentation with a few examples. So first example is a robotic system which is used for assembly. If it is considered as a general system, the input to the system is an image, and the output action will be assembly or manipulation of the object in a particular position. So if the input is image, we will have to extract the 3D coordinates and then do the assembly. So this is a video of such a setup. So what you see is you have a camera mounted on the end effector of the robot, and the camera is used to localize the position of the hole, and the robot is used to assemble an object in the hole. So using the camera, I can get information about the position of the hole and then localize. The problem here is the clearance between the hole and the object to be assembled is very less. So this was an IROS paper which we were worked on. So another work which we have done is a system with camera as well as a laser, 2D laser sensor mounted on the end effector. This is used to pick up featureless black objects from a bin. So what you see here is the setup, and this is the video. So this was part of another IROS presentation. The robot moves, and the 2D scanner is used to get the 2D data. And once the 2D data is combined with the robot end effector position, you can generate a 3D point cloud data, and then you can use it to estimate the pose. But here an interesting thing is a camera is also used. So every time you don't need to scan the setup. The camera, as you see here, at this point takes an image and checks whether if there is an disturbance or not. And if there is a disturbance, you will not pick up objects from there, and then you will pick up objects from another position. So, so let me show here. So one of my friend is disturbing the setup. Now, using the information from the camera, you can detect where there is no disturbance, and then you can pick up the next object from the place where there is no disturbance. So let me pause it here and go ahead. So with these examples, what I want to say is, if you give an image as input to the system, you try to get the pose of the objects from the image. So first step will be segmenting the image, and next will be extracting the pose of the object using the camera calibration data. And once you have the pose of the object in the camera coordinate system, you use hand-eye calibration information, which I will explain later. And then you can actuate the robot to the desired position. The focus of this work is specifically on hand-eye calibration as well as object pose estimation, particularly the segmentation part and picking up. So generally speaking, if you have an input image, this is how you will have a segmented image, and then you have 2D coordinates. And from the 2D coordinates, if you have camera calibration data, you can determine the 3D coordinates and the 3D pose. You can use a 3D pose to do manipulation, assembly, etc. So in a conventional method of pose estimation, first stage, what you see here in the top 3 images, this is the setup we have built for dimension inspection. So the requirement was quite strict. So we had to measure dimension below 1 mm. So we used a customized illumination setup, backlight illumination, and then you can get an output with a standard image processing algorithm or segmentation algorithm. But the case shown below, the object on the left, if you look at the histogram, that histogram will be having a single mode. And if you apply any conventional segmentation algorithm, directly you will get an image which will have a lot of artifacts. So once the region properties are obtained from an image which is segmented, you can use camera parameters and then 3D pose. So segmentation process is error prone, especially when it's an industrial environment and you don't have control over the atmosphere or the lighting system. And for this system, the measurement is made in the camera coordinate system, but the robot is actuating or moving things in the task space system. These are mutually related by transformation X. And if you determine the camera information in camera coordinate system, you have to transform it to the robot coordinate system. So to do that, you do hand-eye calibration, and that process is estimating this relationship X. In the conventional method, what is done is, this is a very commonly seen image, which is, if you refer to any of the hand-eye calibration literature, which is from a very long time, you have a robot, end effector position is depicted by B or B1 here, and the pose of a particular calibration grid or a calibration artifact with respect to camera is represented by A1. In this case, if you have a second pose, similarly, you will have A2 and B2, and you can combine these relationships. That is the relative pose of the camera of the second pose with respect to the first, and the end effector second pose with respect to the first. If you represent it by A and B, this problem can be formulated as AX is equal to XB, where X has to be determined. So the matrices A can be, A1 and A2 can be obtained from the pose of camera, and B1 and B2 can be obtained from the kinematics of the robot. This solution requires minimum, as seen in the figure 2, and for practical reasons, most of the time you require 3 or more kind of information. So the standard steps which you will do if you want to do this hand-eye relationship estimation is, first you will calibrate camera. You will take images of artifact from different poses, more than 3 poses of the robot, and then you will measure pose of the artifact, and you have a pose of the robot, and then you supply this information to a hand-eye calibration algorithm. So what we propose to do is to change or adapt the second and third steps. So the proposed method is, in a conventional industrial robot, it's a possibility that you can define an external coordinate system with respect to the robot, and the problem becomes simpler in that case. the formulation changes to x is equal to a1 t b1. So you are able to estimate x using the information of a1 and b1 given the transformation matrix C is obtained. So in this case, single image of the calibration grid is sufficient to extract this information of x. So you have image coordinates of a 3D grid and the camera parameters. You supply it to EPNP algorithm. EPNP algorithm is efficient perspective endpoint post estimation problem, which is very popular and already implemented in OpenCV. And you can directly get output of the eye-hand calibration information. So instead of the 4 different steps which we mentioned earlier, which I mentioned earlier, this can be done in 3 steps and only using a single input image of a calibration grid. So a 3D grid was obtained so that the post estimation would be more robust. And most of the cases, this information is sufficient for the task which you have to do. The second video which you had seen had used only this much of steps, and the process could run successfully. But in case you need to optimize refine the parameters for X, you can formulate the errors in the image coordinate system and relate it with the refinements which you have to do in the parameters using Jacobian by partial differentiation. And you can use a multiple iterative based refinement technique to refine the estimates. So for illustrating the results of this hand-eye estimation, so the image shown here has a 3D grid, and the image coordinates have been projected. The 3D coordinates using the camera calibration matrix has been projected on the image, and they are matching exactly with the corners which is seen in the image. So if you want to see a plot of the estimated parameters, so for different number of different images, almost 10 images has been taken, and the translation as well as rotation part has been obtained. Those are plotted here. You can see that there is no much of variation between these obtained values for different images also. And so this means that those results are almost stabilizing at the particular estimate. And so this plot is from the experiment which you had seen as part of the second video, where the 2D scans from the 2D scanner was projected on the image using the camera calibration, the hand-eye estimate and the camera calibration information. So these values are matching, and on the right you can see a single scan line and the lines from the scan directly projected on the image which is obtained from the camera. So these lines are exactly matching, which shows that the estimates are quite good. And next, what I want to discuss is the segmentation process. So in the segmentation process, a single approach will not give good results. So a combination of 3 different approaches using Sobel, adaptive threshold, and Otsu's binarization was used. So one of the method, that is Sobel, gives you directional edges, and the adaptive thresholding method gives you local variations, and Otsu gives more of global idea of the system. If you combine all those information together, you can get more better segmentation process. So once you have the segmented images, you try to detect the edges. If there are 2 edges, directly you can extract the sender coordinates, and then you can ask or command the robot to go to the position. But before pickup, one stage of verification by reprojection is done. But most of the cases, there is possibility that there is only one edge that is detected. Now, using the hand-eye calibration information, you can align the camera along the edge and then search for the parallel edge using the input image from that particular pose, and you can determine the parallel edge, and then the same process can be continued. So some of the results for the image which I had shown initially. So results from 4 different algorithms are looking like this. So when you combine all of it together, you get final better results. And then from that, you can detect the edges. And then at the last stage, before just picking up the object, you can reproject the edges and then verify. So multiple such steps are required, because assuming that there is the possibility of an edge or a misdetected edge, you can always verify it and then go to a final process of picking up. So this is a video of the setup. So you have you are a robot, and it is mounted with the camera, and the objects are kept on the table, and then using the proposed method, you can directly get the pose information and go for pickup. And at the last stage, you also check for the force feedback from the robot. So in case there is a collision or some issue, you can abort that task and go for the next task. So these are the practical implementation of the same setup, same process. So what I want to say is the whole process as a whole, when you combine the hand-eye estimation process as well as the segmentation, you can use it successfully for the pose estimation as well as pickup of the objects. So in summary, so I have discussed about hand-eye calibration using a single image and a method of pose measurement using images lacking on contrast, and then experimental validation of both approaches. So so this is this gives a nutshell or a summary of whatever I have discussed on this particular topic. So this brings me to the conclusion and to the end. And if there are any further questions, I can answer those questions.
Thank you very much for your wonderful talk, Ribi. Unfortunately, we're a little bit tight of time. So let me just ask you, did you try using any depth cameras as well for this method?
So I have not used depth camera for this particular method. So the standard procedure would be to use a depth camera, but then you have to do, you have to get the point cloud data and then process it. So using a single camera, RGB camera, would be a little more challenging, and that will be more interesting to solve. So that's why I propose this approach.
But what I meant, maybe I should paraphrase. I mean, like a fusion of your method, which is only visual camera based, and fusing the cloud data, for example, which you can get, or at least some coarse, crude information about the cloud from the depth sensors. Is it possible to fuse the methods?
Yeah. So if you give this problem to any bin picking system developer, that's the solution they are going to propose. And the second video which I had shown involves a camera as well as the 3D information we were projecting and verifying, and so that is a standard solution which is available in industry. So you can readily get it, but then it is very challenging to do it using cameras and very less number of images. So that is my perspective.
I see. Thank you very much, Ribi, for your talk. And I would like to invite the next speaker, who is Olga Borisova, right, presenting about the galloping robots with actuated tail from ITMO University, St. Petersburg, Russia. Please go ahead with your talk.
Hello. Do you hear me?
Yes, everything is perfect.
Yeah, good. Hello, my name is Olga Borisova, and I would like to present you our research, analysis, and modeling of galloping robot with actuated tail for balance. So, robots development for dynamic physical interaction is one of the most significant challenges for robotics. Most of the modern hardware used in robotics came from an industrial application and not very suitable for mobile robots. The most crucial criterion in industrial robotics is motion precision, since the environment is highly structured. In contrast, in the field of mobile robots, the environment is totally unstructured and position control can no longer be used. Especially if we are talking about mobile robots that face an unknown dynamical environment during a high-speed motion. For example, image quadruped has a proper gait pattern, but we can see that it falls when it meets an uneven surface. Therefore, we consider the design of such robots from the point of view of biomimetic principles. Biomimetics is an excellent method to design robots for dynamic physical interaction, since animals are created to handle it. Biomimetic does not mean replication animal's structure, but taking the principles or main features and applying them to the artificial system. Nevertheless, using the principles of biomimetics, we can implement a way to preserve a galloping robot equilibrium in the same manner as land animals with long tails do. Our task is to understand how the tail works to balance and turn in nature and transfer this to our construction, taking into account the mechanics and control system features and advantages. We have already developed the open leg. You can see it here. It's attached to a pole and can move along X-Y axis without rotation. In this study, we added one more degree of freedom, this rotation movement, and it was necessary to stabilize this system. Using biomimetics principles, we can add a tail for providing balance to achieve stable hopping behavior on a slope or uneven terrain without increasing the leg complexity and control system complexity. And this picture, you can see a real cheetah uses its tail during a highly dynamic chase. When the cheetah body tilts to one side, the tail rotates in the opposite direction. Thus, the body tends to an equilibrium position. In this way, the main idea is to find the relation between a robot body orientation and a tail angle. With this connection, it's possible to control the tail to prevent the robot body from falling. So let's consider the equation, the quadruped robot shown here. The robot is simplified for the analysis. This planar system consists of the robot body and rigid tail with a contour weight at the end. The tail is attached with a revolute joint. So the robot represents an open chain mechanism with 1 degree of freedom. Only the tail rotation can be controlled. The balancing is secured during the flight phase, so we didn't take into account the impact forces. Here we use Newton and Euler second laws to express the equation of motion, and after a few operations and transformations with the equations, we get the relation between the body orientation and the tail rotation angle. Here you can see the animation sequence of a quadruped robot simulation with the tail in the left picture. A wrecking ball hits the robot body while it runs, so to simulate external disturbances. A sensor block measures the orientation of the robot's body, and then the obtained equation calculates the rotation angle for the tail. And then the PID controller is used to generate torque to move the tail. The right picture shows how the robot's body orientation changes in time. The big spike is the robot response for the wrecking ball impact, while the rest small plot disturbances are caused by dynamic robot locomotion. The next experiment was run with the hopper designed in previous research. As mentioned before, originally the robot body could move only in plane along X and Y axis without any rotation. Now we add one rotation degree of freedom and study how it's possible to stabilize with an activated tail. We simplify this mechanism for calculations and removed all cranks and levers. Here we have considered two ways to attach the tail to the hopping robot. In these cases, similar equations were performed, but some values are projected to zero. Eventually, in both cases, we get the relation between the body's orientation for the hopping robot with the tail's angle of rotation. The left picture shows the animation sequence for the one-leg hopping robot. The tail can keep the hopper body in a horizontal position of both flat and slope surfaces. As shown in the plot, the robot orientation and tail rotation oscillate around the 0 radian. The second plot shows the impact forces of the interaction with the ground. I would like to summarize the main points. In this study, we managed to maintain the balance of the galloping robot and the hopper by adding a rigid tail to the structure. The tail generates a torque using the derivative ratio of angles. The result is that the control system of the tail ensures the keeping of the balance. And finally, the simulation results show the effectiveness of the actuated tail for stabilization. And that brings us to the end. I would like to thank you for your attention. And if anyone has any questions, I will be happy to answer.
Thank you very much, Olga, for your wonderful talk. So first, let me ask a question from the audience. So the one question reads that Spot by Boston Dynamics doesn't have any tail, but it is able to maintain balance. Can you have any comments about it?
Oh, okay. Let's see. Oh, I have an interesting example. You know, there are some cats without tails, bobtail, or wildcat, or bobcat. They don't have any tail, but they manage with this life, but not very good, like cats with their long tails. So our method providing balance is one of the way. So Boston Dynamics don't use tail, they use other methods. we consider this way because our system work in high speed locomotion, and our system is underactuated. So I think so.
Okay, thank you very much. And also another question was, have you simulated the reaction of the robot with different tail orientations? So I guess the behavior of your robot, if you orient the tail differently.
Yeah, we was ran some experiments, but the other place of the tail did not work very good. The robot worked a few seconds after all it fell down. So we didn't include this experiment.
I see, thank you. And maybe one quick question from me. So when you showed the simulations on when the robot was jumping on an inclined surface on a ramp, right? So the goal was to maintain the vertical balance, correct?
Yeah.
But probably in this case, you'll be slowly going down, descending on the ramp, correct? If you don't control the global position of the robot. But with the tail motion, is it possible to not only maintain the verticality, but also to maintain robot's position on the ramp or make it move left and right?
Yeah, we can which position we write in the control system. Our system will be make. In our experiments, we use the position, a horizontal position of the robot's body. So the control system keeping it. If you want any other position, it also would work.
Okay, thank you very much, Olga, for your talk.
Thanks.
Thank you. And I would like to invite next speakers. So I think it's Sergey Savin, right? And also the authors of Lyudmila Vorochayeva from Southwest State University and Hani Hamid of Innopolis University. Sergey, you have the floor. Please go ahead with your talk.
Thank you so much. And apologize for giving the third talk in a day. I imagine it gets boring after a while. So, listen to me, I mean. So I'll try to be quick. This time I'm representing a work which is spearheaded by Lyudmila Vorochayeva and her group, where I happen to be a part of. There is an ongoing number of projects which are all collectively represented by the desire to learn how to control multi-link robots with a reasonable number of links, which we'll come back to in a second. But multi-link robots with a reasonable number of links and rigid links via exhaustive description of stages of motion. That is the direction that the group takes. And the group attempts a lot of ideas, which I'll again discuss quickly in the presentation. But it ranges from jumping robots to crawling robots to swimming robots and semi-walking robots. A lot of those. And the idea is still the same. Describe them explicitly using exact representation of each stage. That works, and it works in interesting ways, allows you to say exact things about certain stages of motion. But in order to appreciate the whole body of work, you would have to go through a number of papers because of the exhaustive nature of the research. You have to try to see each particular aspect, and it takes a lot of space to describe. So that I apologize if this limitation of the approach bleeds into this presentation, where there'll be too many details for a short talk, but in any case, that is my overview. Now to go into particulars. Let's say we have crawling robots. So they can be rather complicated as the two robots, one in the center, one on the left. Or you can make a crawling robot rather simple as one on the right, which was designed in the Institut Проблем Механики. Don't want to butcher the English name. And was tested a while ago in Southwest State University. You can have those vastly different structures, and some of them can actually be explicitly described in terms of each particular stage the motion takes. Of course, you can just give up on the idea of stages of motion and just do trajectory planning, which is a typical approach in modern robotics. However, splitting it into stages allows you to give more detail and more control over what exactly you expect the robot to do. That is the direction the study takes. Now, let me just give an example of what we mean. Let's say we want to overcome obstacles. So in fact, what you can do is split this whole procedure into different different stages. Here are just few of them. There are more than what is shown. As you can see by now, like internal numbers, there are like 12, etc. It is those are just a few of the stages the motion takes. But you can see that the motion can be divided effectively. And dividing motion like this allows you to say what happens during this stage. Sometimes the robot dynamics can be actually represented by a single differential equation during some of the stages, because contact interaction during this stage cancels out a lot of the dynamics. And if you remember my previous talk, we talked a lot about contact interactions and how we model them. Here, the approach allows you to avoid this whole discussion by saying contact actually in this stage completely allows you to completely neglect some aspects of the dynamics. For example, one link is just stationary on the ground, so its dynamics is irrelevant. Instead, you get dynamics of the other joints as a smaller number of differential equations. So this is the approach. And when you consider stages of motion like this, in this fashion, what it leads to is you can actually develop a gate as something like a finite state machine, switching between different stages. And you can focus on conditions when one stage is over and another one begins. All of those questions are answered in the previous works by Lyudmila Vorochaeva and co-authors. Here's one example from one of the papers, I believe, written last year. I think it was published this year, where you discuss how exactly the motion takes place and where you can even arrive at a singularity position. So, but it requires a lot of parameterization. You have to parameterize positions of the links, etc., at each motion stage, especially if you want to use minimal coordinates for each and single stage of motion. Now, all this is challenging, but it can be made even more challenging when you start to consider the fact that your control is sometimes based on events which are discrete. So, for example, here, what we see is a diagram for friction control. What does it mean? Well, the robots that we considered previously, actually for them, it was proposed to use a device which can control the friction coefficient between the ground and the robot. Basically, you have a special pad which goes down to increase the friction, or it goes up to decrease the friction. This pad is considered a discrete event, and choosing when the pad should be up or down is a control. So you get this discrete control sequence. And this kind of thing goes through every stage of motion. And you, on top of having conditions between the stages, you also have to choose when you activate this this pad. If you want to avoid transient conditions, etc., you can assign this pad to go up or down once during one stage. This would allow you to neglect some of the dynamics and make simpler conclusions about what is going to happen during the stage of motion. But you don't have to do that. That depends on what you want, more dynamic motion or more slow and stable motion. But that is just to illustrate what kind of approach this whole thing represents. Now, in this paper, Ludmila posed a question, which type of robot suits best for a crawling motion forward? So since a lot of the robots were studied previously, now it was posed how, like in terms of those different separate stages of motion, how you can choose the best structure. Of course, those structures would have different performance on different stages. That is kind of the nature of this discussion, this approach, etc. So here, what you see is a simple example of a 3-link robot, which has 2 joints. That is a simple structure you saw in a physical example of that robot on the second slide of this presentation, or the third slide. All right, next, here's the alternative. You have additional 2 joints, so total number is 4. And the reason you have those extra 2 joints is to be able to lift up the legs of the robot, so the lateral links. Why? Well, to avoid friction. That is, it comes back to the discussion of having friction pads. You can have friction pads in order to increase friction in the contact points, or alternatively, you can just lift the legs up. And that should provide a very similar effect, except now you also lose parts of your contact surface. So your contact support polygon, as we say in bipedal robotics, becomes smaller. So this is a different type of robot. And this robot is designed to move by lifting the legs up. Of course, it can move the same as the previous structure, but then the additional mass of having 2 extra motors will make it definitely less interesting. So it would have to move in a more complicated fashion to actually, make sure it was worth increasing the complexity. Now, next one is an extra complexity layer. This one has each link as a telescopic link. Basically, there's a linear motor installed in each link. And now we pose the question, can this structure be better? This structure can increase the length of the links, which could be useful when overcoming obstacles, for example. But it has to work also when you move forward, etc. Of course, all those types of motion, like for example, overcoming obstacles and moving forward and moving backwards, etc., they would have different characteristics, and that is exactly what is explored in the paper. Just to avoid, blowing up the talk into infinite number of time, I would try to be quick. I would just demonstrate one conclusion that was one type of thing that was found. And I would leave the rest in the paper so you can see. But here's one example. So they considered motion forward. And what they found is that there was one regime in which structure number 2 could actually maintain a constant time for finishing this stage of motion. The stage is when the lateral links kind of move this way from being, behind the robot, they move in front. I mean, that is just the one part of the gate that the robot has. So it was possible to actually have a constant time for this motion, even when the friction coefficient is changing, and we are talking about the best possible time that is available without breaking the friction coefficient. So it was possible to find a gate which would still maintain the speed for a range of friction coefficients. For different robots, it wasn't possible. However, of course, this presupposes a certain type of gate. So, for the details of what type of gate, I would again have to invite you to the paper, which has a diagram, I believe, for the gates. So anyway, this is just one experiment. There was a number of them. And since this is this part of the contribution is specifically completely done by Ludmila Varachaeva, I don't want to present it as something I did. So I would like to keep it short. and would direct the questions about this to Ludmila. That is her personal work, which had been shown very interesting. Here you can see conclusions after analysis of those structures for in terms of advantages and disadvantages. As you can see, the disadvantages for second, third type are mostly about complexity, but you also have those recoils, which is discussed again in the paper. And at least in for some gates, you can see that the second structure was more advantageous than the first and the third. Whereas, for example, for overcoming obstacles, the third one is obviously better. So you have those mixed conclusions, but that actually represents the nature of designing those robots. It was shown, at least I think 5 years ago more, that for 3-link robots, there is an optimal strategy for choosing speeds of moving the links. But at the same time, it was shown for the simplest 3-link structure. Like, I don't think there was the same type of argument made for different structures. So if you want fastest motion forward, for at least a simple 3-link, you get the answer. For other ones, I don't know, maybe we can, maybe there is some similar result in the literature, but not the one that I'm aware of. So it is a trade-off, and details of this trade-off you can find in this paper. I would like you to direct your more detailed questions to Ludmila, but I can try to answer maybe general ones here. Thank you for attention, and sorry for keeping your time, third time this day. Thank you.
Thank you, Sergey. And I don't think you need to apologize. Thank you for an interesting talk. We are almost out of time, so I just have maybe one quick question from me, if you don't mind. So I can easily understand how you can, benchmark robot movement velocity, for example, right? When you can just check the maximum speed on the condition of that you don't lose friction, from what I understand, right? But you've also mentioned that the robot must be maneuverable, must be able to go through confined spaces, for example, and step over obstacles. So I'm just curious, what kind of benchmark, what kind of cost functions you used when you were talking about, for example, stepping over obstacles, or checking the maneuverability of your robots?
Yep. That is actually simple to answer. So, for example, when let me just give one answer to one simple situation, and everything else is kind of the same. So let's say you go through confined spaces. So for those robots, you can actually define a number of gates which can pull them through those confined spaces. And those gates would have to result in your robot moving from point A to point B, obviously, right? And for those gates, for let's say a 3-link robot, you would have a parameter which would, depending on how you choose it, would eventually characterize how much your links can move and how much a displacement of a center of mass you can achieve with that. And for some types of robots, it is even possible to find a confined space where you wouldn't be able to move at all. And it's probably not surprising from a physical point of view, but maybe from mathematical one. But in any case, you can simply set your width of your space, for example, as one of those parameters, and then you can find the relation with the parameters that define your motion at the stage. And you'll see a clear difference between different types of robot or different gates even. And that's how you basically analyze it, at least in this framework that was proposed in the paper. It's definitely not the only one, but no, that is how it is. You propose parameter, define everything in terms of this parameter, and then make conclusions on the ranges, etc.
I see. Thank you very much, Sergey, for your talk and for your answers. And I would like to invite the last speaker of this session, so Chun Ta Chan, and from the group, also the paper authored by Mikhail Vartanov and Sergey Petokhov from the Moscow Polytechnical University. So please go ahead, and you have the floor.
Good morning, Chairman, everyone. First, let me introduce myself. My name is Chumda. I'm studying PhD at Faculty Engineering in Moscow Polytechnic University. My supervisor is Doctor of Science, Professor Vatanov, and the second is Dr. Philosophia, Associate Professor Petukov. What I'm going to talk about today is the topic, experimental research of robotic assembly process using a fast route signal and low frequency vibration. In this presentation, I have 5 main points. I'll start with the overview of the method to improve the technological reliability of the robot assembly. Then I focus in experimental and finally conclusion. First of all, I'd like to give you an overview of the technological reliability of the robot assembly. The process for the induction of assembly automation in the industry is largely determined by the reliability of assembly process. In order to increase the technological reliability of the assembly process, various physical and technical effects are applied. The efficiency of rotational motion and the use of low frequency vibration are the most promising areas in the field of automatic assembly, which is confirmed by the result of theoretical and experimental works. The article presents the result of an experimental study using the rotational movement effects and low frequency vibration of the part in order to reduce assembly effort and the probability of the part jamming. A mathematical description of the assembly force components were obtained using statistical experimental design. Let's move on to design of multi-factor experiments. To begin, we choose a kinematic assembly scheme, a dynamic model of the process of assembling of cylindrical joints were constructed using industrial robots and vibrational device. The robot gripper can rotate around its vertical axis, and the vibrational device has tooling. Each link of it being driven by the separate drive. Secondly, I will focus on the determining of the process factor. The 5 parameters in the table were taken as input parameters in the study of system. All of them meet the appropriate requirement of the controllability and integrity used to factor. Next, the type of model of the response function is selected by the equation of power type. Level of factor and variable interval were presented in the table. The factor varies as 2 levels. Lastly, the factorial design of the experiment were chosen. It reduced the number of experiments to 16. Experiments or experiments according to the principle of randomization were carried out in the random order. Let me turn now to experiment. Now I want to describe experimental equipment. Its general view is found in the photo. A four-torque sensor 2 were installed on the output link of robot 1. The device buzzing switch equipped in the vibrational device 7. The start 5 were held by the gripper 3. Vibration were provided by the low frequency generator 9. The low frequency generator were controlled by electronic frequency meter 8, and the actual vibration amplitude of the operational device were monitored by contactless laser sensor 4. All sensor signals were collected and processed by the computer. Thus, during the experiment, continued monitoring of current value of the technological factor were ensured. Next, we consider experimental result. Utilize how the experiment result of dispersion and force, division of forces and torque. Single experiment saw sample were a shaft. Then in the experiment, 4 components of the force and torque were investigated. By using statistical experimental design, the dependence of force and torque on the factor of the robotic assembly process were found. The slide shows the dependence of the 4 FPS on the various factors in the assembly process. It is clear that the vibration frequency and the vibration amplitude and the linear velocity are proportional the force FPS figure IBCD. On the other hand, the angular velocity and the gap in the zone are inversely proportional to force FPS. We'd like to conclude that the conducted experiment proved the presence of the effects of vibration and rotation on increased technological reliability of the assembly process. Further research will be associated with a change in the zero level of the variation in the of the input factor. That brings us to the end of my presentation. Thank you for listening.
Thank you very much, Chinta, for your talk. And I think we have time for one question. So we had one question from the audience, which was, why was factorial order DOE selected? Are there any other methods that you could use?
Sorry. Would you like? Could you repeat?
So the question was, why was a factorial order selected? And are there any other alternatives to this?
Which other? I'm sorry. I think I don't understand your question.
So maybe so the Ribi who asked this question in chat can elaborate a little bit more on this. But the way I understand is, I think on the either next slide or one previous slide, you mentioned that you could have reduced the number of experiments from 16 to 1 or something like this. Is that correct? Yeah, this one maybe. Yeah, so the fractional factorial design, right? So I guess the question refers to this, yes.
The method design of experiment you know the process assembly depend on monomer of many factor parameter. We choose 5 parameter E and conduct experiment.
Okay, yeah, I think this probably this answers the question, and I would like to encourage the audience, if you still have any questions left, please feel free to contact the authors and feel free to elaborate more in the discussion outside the conference, because we are out of time right now. So thank you very much, Chunta, for your presentation. And I would like to thank all the presenters and all the audience who's been here for your kind attendance. And now I would like to announce that there will be a lunch break, and we'll resume our sessions at 2 p.m. Moscow time. So I hope to see you all there, and have a good day. Thank you again, Chunta.
Thank you.
Presenters. All presenters are here. Do you have the presenter of first paper? Do you have Victor, Ivan, Natalia, or Andrei? So probably we don't have a first speaker. From the second one, do we have the speakers of the second paper?
Yes, Elias is here.
Okay. Okay. So the third one. Let me check. So we'll check this. Okay, for the fourth one, Oleg, Semyon, Igor, who will present the paper. And the last one, Roman, Ivan, Olga, Sergey.
Yeah, I'm here.
Okay. So let me ask again the first speakers. Are there anyone to present it? So if there are no speakers for the first paper, I propose to start with the second one. I would like to introduce Ilyas Tursunbek from Nazarbayev University, who will talk about modeling and simulation of spherical parallel manipulators in Calput Sim robot simulation software. So please, you have 10-12 minutes for presentation, and we'll have rest time for questions.
Okay, hello, thank you. I hope you can hear me and see my screen, yes?
Yes, we can hear you, we can see your screen.
Okay. My name is Ilyas Tursunbek, and my co-author is Dr. Almashin Timirov from Nazarbayev University, Kazakhstan. And we'd like to present you our work titled Modeling and Simulation of Spherical Parallel Manipulators in Capella Sim Robot Simulator Software. It is widely known that parallel manipulators usually have more complicated kinematic and dynamic analysis compared to the serial manipulators, and simulation tools are widely used for kinematic and dynamic modeling, motion optimization, performance evaluation, and control strategy verification. Some well-known examples of simulation tools include Gazebo, widely known universal robot simulator software compatible with ROS. Webots primarily focuses on the simulation of of mobile robots. Robotic used for simulating serial type, industrial type robots. Atoms is used for dynamic simulation of various different machines and mechanisms. And Capella Sim is another type of universal robot simulator software that we believe is much easier to learn compared to Gazebo. But one of the issues with that is that it has limited literature and some tutorials how to use that, and it has limited applications in research, at least in the papers. So, so we decided to use it in our research because it's easier, and we faced the problem, and we are trying to solve the problem. Like we want to describe how to use it and show some research applications. And there also exists some simulators specifically targeted for like specific type manipulators, but mainly you have to, if you're doing research, you have to kind of create them yourselves. For example, the Hexavis software, it's specifically like some commercial software specifically targeted for hexapod simulations. So our work aims to present a new methodology for modeling and simulation of spherical parallel manipulators, shortly SPMs, in Capella Sim, formerly known as VREP, using SPM with coaxial input shafts. Shortly, coaxial SPM is the case study. So this work originated from the need to simulate SPMs that we are working with in our research. And here you can see the example of the simulation model in Capella Sim that we're going to talk about later during the presentation. So, but before going into details, let us first talk about what is SPMs. So shortly, SPMs are capable of 3 degrees of freedom spherical motion. Their workspace is a fraction or sometimes full sphere, but usually they have limited range of motions for some degrees of freedom. For example, Agile Eye, developed by Gosling, has 140 degrees cone opening, and then plus minus 30 degree of the rotation of the mobile platform around itself, around its own axis. Similar to the Agile Wrist, it's a kind of a load-carrying enhanced version of the Agile Eye. So both of them have limited rotation of the mobile platform around its own axis. So but in some applications, such performance is desired. And one of the SPMs that is capable of that is coaxial SPM that we are actually investigating in our works. So to do the manipulators study, you need to, of course, start with the kinematic analysis and workspace analysis. And for those stages, you need a singularity detection and link collision detection. Singularity detection can be done using the theoretical equations that you derived for the forward and inverse kinematics. However, for the link collision detection, you can do that as well. But if you do the approximation of the links, it can result in a lowered precision of your workspace. So another approach is to use some simulator softwares, as we do in our research. Some examples of the parallel robots implemented in KPLSIM are double hexapod and adept quattro. So this is kind of built-in examples in the KPLSIM software, but it's not only the examples, but all of the examples of the parallel manipulators they have are mainly translational robots. But we are focusing on the spherical robots. And before kind of creating the model in the KPLSIM, first of all, we need to do the kinematic analysis. So we did the kinematic, we did the study of the kinematic model of the coaxial SPM. Here you can see that. So it has mobile platform connected to the base 3 via 3 legs, each leg composed of 2 links, proximal and distal. And the geometry of those links is described by angles alpha 1, alpha 2. The geometry of the mobile platform can be described by angle beta. So 3 angles, alpha 1, alpha 2, and beta are main parameters for the design. It can be used for design optimization, of this manipulator. The final orientation of the mobile platform can be described using 3 vectors v1, v2, v3, directed from the center of the rotation. And inputs are provided to the actuators located on the base, but it can be simplified down to the actuation of actually the proximal links. So then we did the forward and inverse kinematics studies, and we found out that there exist several solutions for the forward kinematics, and same situation for the inverse kinematics. And whenever you do the control in the future, of course, you want to have a unique single solution. And in our previous works, we kind of developed the algorithms for finding and for selecting that single solution, for sticking with a single solution. But you want to, of course, check them in simulation before applying on the real experimental prototype. And when you do the workspace analysis, you also want to eliminate situations when you have some link collisions. And for that reason, we used KPLSIM. So we started with the creation of the model in SolidWorks CAD simulation software with the following parameters: alpha 1 45 degrees, alpha 2 90, and beta 90 degrees. So you can see the SolidWorks model here was the stage first step in creating coaxial SPM model in KPLSIM. It should be saved as STL. Then you need to import that STL file to KPLSIM. Then you need to separate links, do mesh division, and reassemble the model, like placement of the initial placement of the links. Then you need to, of course, reorient the model to to match the coordinate system you're using in your equations. And then you need to create a correct scene hierarchy by creating 2 closed loops. This is a closed loop kinematic chain, so you're simulating that same kind of behavior, same architecture in the model. And then you need to activate kinematic module by enabling and setting IK groups. Then you need to activate collision detection module, and then you need to set up interface with MATLAB, or it can be anything like other external APIs such as ROS with Python scripting. And all of the details are described in the paper that we submitted. I skipped I omit the details because most probably they're gonna be too detailed and not very interesting. So this is the main kind of algorithm to follow. And here are some examples. For example, if let's say we have input joint positions theta 60, 90, 120 degrees. So it's 3 angles that you use to actuate the SPM. If we using the equations that we derived that are presented in this presentation, we found that, for example, the orientation of the mobile platform vectors v1, v2, and v3 can be found as follows. And for example, if we simulate same orientation, apply the same angles in the simulator, we observe those angles. So those angles are not angles; those vectors are were taken from the simulator software. So you see they kind of match pretty close to each other. On the figure 12, you can see the manipulator trajectory for each vector from the home position to the final position set by angles 60, 90, and 120. So here with the solid line, you can see that it's calculated values, and then with a dashed line, it's simulated values. So they also match pretty similar to each other. So, for example, if you're interested in the link collision, you can. Here's the example of the link collision event. So you can see that links kind of change the color. So this collision flag can be sent to the external API. For example, in our case, it's MATLAB, and that can be used for some desired applications. Here are some examples of the of the simulation of the coaxial SPM without collisions, and they are visually, at least at this stage, verified with the experimental prototype. So this result can be used, and it was used in our other study. So we were studying the space of physical configurations of the coaxial SPM for future generation of optimized trajectories. So we tested, we started with this space of physical configurations, and then for each case, it's a numerical study. So for each case, we did singularity detection. This is the whatever is left after a singularity test, and then the remaining test nodes were sent to Coppelia SIM for verification for the link collision. So this was done using the Coppelia SIM, and later on, for example, this result, this can be used for generating some optimal control strategies. For example, we're working on the development of the joystick control of the model, of the simulation model. Is different from the paper because we did it actually before, and we are redoing it. So yeah, it can be used there. So in conclusion, in our work in our work, we presented the methodology for modeling and simulation of the coaxial SPM in Coppelia SIM software. Then we did preliminary experimental verification. And then we also showed that the proposed methodology allows accurate simulation of the spherical parallel manipulator we are studying. And this can be adopted for modeling the motion simulation of the closed kinematic chain robot systems. And in the future, we are planning to generate, we actually did it, generation of singularity and collision-free workspace for motion control and path planning. It can we can implement the inverse kinematic mode control in Coppelia SIM. We can do the optimized joystick control, and those kind of simulations in Coppelia SIM can be used for developing several different learning algorithms. So this is it for my presentation, and thank you for your attention.
Thank you, Ilyas. If anyone have a question, please type them in the chat. I will post them to Ilyas. So while we're waiting for the questions, I can pose from my side. Have you studied time delay for teleoperation you use with the joystick, and how critical is it?
So we didn't study that yet, but it's currently it's not very suitable for online applications, because we are using MATLAB, and it introduces some delays for the control. But we are migrating. We are slowly moving to that to ROS and Python, and with the preliminary test, we see that it kind of matches, but we didn't really did the time measuring, and it's important for it depends on the application you want to do. It's important, of course, But for example, if you want to do it like in the future, we want to use that manipulator for the like we want to put it on the mobile platform and test it with like in a more dynamically changing environment. In that case, to stabilize some objects, and in that case, yeah, that can be very critical.
Okay, thank you. I have another question. So you studied a lot singularity of the manipulator you presented. Have you understood the issue of deformation under the static and dynamic forces? Because in practice, that might happen that you will not be able to reach kinematic singularity because of the deformations, and you will have collisions or singularities much earlier.
Yes, I agree with you. No, we didn't do that study because we are still on the stage of like setting up. We want to fully understand the properties and the behavior of the coaxial SPM and its like infinite rotational capability of the mobile platform. And then after we like to do the like those studies as you mentioned. But initially, using the experimental prototype, yes, we see that it was 3D printed, and then those deformations cause some problems for us that don't match with the simulation.
Okay. Thank you again for your presentation, and we'll go to the next presentation. Do we have the presenters of first paper? Victor, do you, or someone else from the first paper? Okay, if no one appeared, so we go to the third paper, and I will ask Stanislav Michel to present, representing Innopolis University, to present a paper that will address algebraic approach to the stiffness model reduction for manipulators with double encoders. Please use 10-12 minutes for presentation, and we will have 3-5 minutes for the questions after all.
Okay, hello everyone. Can you see my screen?
Yes, we can see your screen.
Okay. Well, hello one more time. My name is Stanislav Michel, and I would like to tell you about algebraic approach to reduction of stiffness model in application to robot with double encoders. First, let me explain what the double encoder is. Generally, it's the measurement system that consists of two encoders that placed on the same axis, one on the motor side and one on the load side. Difference between these angles can be used in different problems, for example, to control robot with elastic joints or to estimate the external torque. But in our work, we would like to use this information for compliance error compensation. In order to compensate the robot deformation, we first have to define its stiffness model. There are different techniques for stiffness modeling. Here we would like to use virtual joint method. It assumes that we can introduce elastic elements for links and joints of the robot, and use the deflections in order to describe the total deflection of the robot tool. In particular, we can define Cartesian compliance matrix in order to find the end effector deflection, and this matrix can be found from the compliance in joint space using the matrix of stiffness matrix of robot and the Jacobian with respect to virtual joints. If we would like to work with double encoders, we need to simplify this model. In particular, we can assume that the links are rigid and all elasticity is located in joints. So in this case, we need to define a so-called reduced stiffness model. The equation is almost the same as previous, but now we use more simple metrics that that define only compliance in joints of the robot. And we can use it in online, for example, trajectory compensation if we know some predefined trajectory and our estimation of the model, then we can calculate new angle value using information obtained from the about contours. Typically, parameters of reduced stiffness model can be obtained from experiment. In this case, we first need to define equation for the tool deflection in form of such product with matrix A and vector P, where vector P contains compliance of reduced model. Then we take a different measurement of tool deflection under the applied external force in different robot configurations. And after that, we can define estimation of the robot parameters, for example, using least square technique. In this work, we would like to show another approach where we try to estimate reduced parameters using mathematical description of links. I mean, if we already know metrics, stiffness metrics of links, that we can, from this information, estimate reduced model. So our goal is to find such parameters of stiffness that we will have almost the same Cartesian stiffness that we can obtain from the full stiffness model. Let's apply the following transformation to the both sides of this equation. We can rewrite it in form as a vector, and in this case, we will have product of vector of internal matrix with matrix B here that is equal to Kronecker product between two Jacobians. Then the problem can be formulated as a minimization problem between such equation where vector subscript G and L defines part of Jacobian that corresponds to joints or links respectively. Delta is difference between our reduced model and the real stiffness that was used in full model of the joints, and the KL is a vector of stiffness for links. Solution of previous equation can be defined as a matrix equation where all mjj int mjl int are quite complex expression that can be obtained using integration for all the workspace of the robot. For sure, the result equations are quite complex, but it can be a little simplified. In particular, we can regroup columns of Jacobian in such way to have submatrix that consist of columns for joints, then columns for first link, second link, and so on. In this case, the first matrix MJJ, each element of this matrix can be found as simple dot product of two columns of this Jacobian in square. And for matrix MGL, indexation is little more complex, but idea is the same. We just take one column from J joint and two columns from J link that corresponds to index of stiffness parameter for these columns. By the way, this method depends on Jacobian, and during this work we defined another algorithm for the Jacobian estimation. Its main idea is to find find initial value for variable matrix T as product of tool transformation with inverted rotation matrix for the robot in general. Then use homogeneous transformations matrices from end effector to base, and calculate columns directly from this variable T matrix using rows of this matrix and elements in right column of it. In order to compare our method with experimental technique, we used modeling of the robot parameters of this free link manipulator you can see in the table. And the results are following. We have almost equal values for stiffness in both cases, and the error in position is almost equal to each other. So we can say that these two approaches both can be used for reduced stiffness model estimation. Of course, all of them has their pros and cons. In particular, for experimental approach, it's much easier for implementation. Also, it's based on the real robot data. But this method will depend on set of configurations that we use, on measurement errors and other experimental problems. On the other side, analytical approach is more complex. It requires knowledge of link stiffness parameters if we want to find stiffness matrix of reduced model. But it covers all the workspace, so it doesn't depend on robot configuration, and it can be used in order to analyze influence of each stiffness parameter to the final stiffness in a reduced model. So this is all from my side. Thank you for attention. I am ready for your questions.
Thank you, Stanislav. Thank you for your nice presentation. We don't have questions from the chat yet, so let me ask you a couple of questions. So you present this approach and show efficiency for geometric modeling, for stiffness modeling, and how efficient it can be the way to compute the Jacobian for dynamic modeling.
For dynamic modeling, sorry, could you repeat the question? I don't catch the idea.
So can we use this idea with the Jacobian computation for dynamic modeling? So in dynamic modeling, we also need to have transfer from joint space to Cartesian space if you want to change, for example, the parameters we want to use, and how efficient this approach will be related to dynamic modeling.
If you mean the Jacobian calculation, it has almost the same efficiency as the classical Jacobian computation algorithm when we use cross product of current axis of rotation and vector from current position to the end effector position. So it's can be, it has the same efficiency in both dynamics and statics.
Okay, thank you. Stas, are there any other questions? So I do not see, so In this case, I propose to move to the next presentation. So,
okay, thank you.
Please let me know if the speakers from the first paper will appear in the section. If no, so I propose to move to the fourth paper that will be presented by Oleg Balakhnov. So Oleg, you from Innopolis University as well. He will talk about a preliminary study on slug-free model prediction control of twist string-based antagonistic joints. So Oleg, you can share your screen.
I'm here. Yeah, microphone, okay?
Yeah, we can hear you. You can share the screen. You will have 12 minutes for presentation, and we'll have 5 minutes for questions later on.
Okay, demonstration ecran. Okay.
Yes, we can see you. We can see your screen.
Hello, my name is Oleg Balakhnov. Let me present the paper, preliminary study on slack-free model predictive control of twisted string-based antagonistic joint. The actual joint is a fundamental element in robotics. This model is used in various engineering applications, including industrial manipulators, walking robots, exoskeletons, etc. Basically, DC motors are very fast and weak and usually require some transmission to use them in robotics. However, most gearboxes have the following disadvantages: low breakability, low shock absorption, high inertia, friction, high weight. These drawbacks greatly limit the scope of the applications. For this reason, alternative approaches are still being developed and explored. One of these approaches is twisted string actuators, or TSA. In TSA, a rope or string is connected to a rotary motor at one end and to a load at another. Motor rotation causes cable shrinkage. If the motor is rigidly mounted, string's contraction will be translated to the load and pulling it towards to the motor. The string contracts with twisting in a nonlinear fashion. Contraction rate is slow in the beginning and grows with increasing angle of twisting. Some of TSA advantages, including the flexibility, intrinsic compliance, light weights, low cost, and simplicity on manufacturing. However, there are several issues related to TSA implementation that should be considered. Possibly the biggest drawback of TSA is the unidirectional nature of actuators. The inability to produce pushing forces is a common property of most cable-driven systems, and therefore tension loss on cables, tendon slacking, which always degrades system stability and its capabilities to accurately display forces. However, the previous works were concerned with application that required comparatively slow motion with maximal frequency of periodic trajectories not exceeding 2 Hz, and therefore did not account for cable tension loss. This fact has motivated us to develop a control framework that will explicitly take into account constraints on string tension while tracking desired trajectory. In this work, we propose an MPC-based control approach suitable for slack-free simultaneous position and force control of TSA-driven linear antagonistic joint and compare it with conventional unconstrained MPC. The suggested method supports a great viscoelastic model of twisted strings with variable stiffness. This is a schematic image of this system and equation. Tau is DC motor generating torques, I inertia, moments of inertia, payload, mass, K and B, variable stiffness and viscous friction coefficients, and F external force. Tension on the string, while taking into account the unidirectionally, can be calculated as follows. You can see that in some cases, the tension becomes zero and the system becomes uncontrollable. We will try to prevent this situation in this paper. Our goal is tracking position of the middle of spring here and the tension. In this paper, we have compared two tracking algorithms, unconstrained MPC and MPC with constraint expressing cable tension. The algorithms will be compared on the trajectory following problem. Since we will use discrete control algorithms to solve the problem, we need to perform preliminary transformation. We linearize the nonlinear model near the nominal values in order to obtain the following error dynamics. Then we discretize the dynamics using first-order Euler approximation. We propose to modify the trajectory online, and therefore we can use an MPC based on solution of quadratic program. Since required trajectory magnification can be considerable, we must use a sufficiently large horizon. In addition, transmission ratio can vary by an order, which constitutes a significant nonlinearity. To tackle this, we will use linearization along the desired state control pair. This first controller, the first controller is the MPC that minimizes deviation from reference trajectory and desired control inputs. In this algorithm, we wrote down only the equation of error dynamics into the QP problem in constraints without other condition. And next, we accounted maximum motor torque and constraints expression cable tension. As a criterion to detect tension loss, we propose to use the variable that corresponds to cable stretching. Constraint expression cable tension is also nonlinear, and therefore we linearize it along the trajectory as well. The QP problem in this case can be stated as follows. Now we can produce the numerical evaluation of both MPCs. In the slide, we present simulation result of unconstrained and constrained MPC when tracking desired trajectory of the spring midpoint while maintaining predefinition tension on it. We carried out a series of simulation on a mathematical model described in MATLAB. The same model parameters were selected from our previous experimental studies involved twisting string actuators. First, unconstrained MPC. At low frequency, error is small. This is at low frequency, error is small, but at high frequencies, we see a sharp increase in error. This is very clearly visible on 4s and 5s graphs. This is because at frequency of 2.4 Hz, there is a loss of tension. In these algorithms, we wrote down only the equation of aerodynamics into the QP problem in constraint and see big error in this case. Constraint MPC for the first three graphs, the error is identical to unconstrained case. There is no loss of tension of them, and the algorithms behave identically. On the last two trajectories, there are sections in which the tension is zero. However, our algorithms change the trajectory so that deviation from it is minimal, but the loss of tension does not occur. As a result, the error for the last two cases is significantly lower than in a constrained case. You can notice that the constrained MPC is slightly increase desired tension, red graphs. Desired tension to support better position tracking, whereas a constrained MPC could not satisfactorily track either. This slide shows the result in the table. For low frequencies, the error of both algorithms is small and practically the same. But for very dynamic trajectories with a weak spring tension between the load, the algorithms preserving the tension of the springs showed the significantly lower RMSE. In this work, we have proposed a model predictive controller for a TSA-based antagonistic system. With this control method, we could modify the trajectory online such that cable tension could be preserved at all times while trajectory deviation was minimized. The proposed MPC method enabled tracking of periodic trajectories with high frequencies reaching up to 2.7 Hz in simulation. We are hoping that the method will pave a way for antagonistic control in more complicated multi-DOF TSA-based systems that require high-speed actuation and accurate tension tracking. The next step of this research is its experimental evaluation on a practical agonistic setup. Thank you. That's all.
Thank you, Oleg. So we don't have questions in the chat. I will have one. So can you give some comparison of twisted spring actuation with respect to variable stiffness actuation? The principal difference, what are the benefits?
There exist several realization of variable stiffness actuators at TSA. Here I haven't examples, but yeah, in this case you have, if we look at the dynamic equation, we can see that K in tension it's K is a variable parameter, and we can because we have two actuators, we can design any stiffness that we want, and this research, there exists several research about this. Yes, so we can realize variable stiffness actuators based on antagonist TSA system.
Okay. Thank you. Are there any other questions? So if not, thank you again for your nice presentation, and we will move forward. So for the next presentation, do we have the authors of first presentation? So no, no one appeared. So in this case, I would like to invite Roman Zashitin to present from ITMO University to present the work on the energy efficiency in legged robots locomotion, open versus closed chains. So please use your time to present.
Hello everyone, my name is Roman Zashitin. Today I want to present a project energy efficiency in legged robot locomotion, open versus closed chains. Quadrupedal running is an enduring challenge in the field of robotics. The main advantage of legged robot over wheeled is the ability to traverse on uneven terrain due to the use of intermittent contact and an ability to shift the center of mass relative to the contact location. That is provided by the lag mechanism that allows using such robot in a variety of fields. This study is more interesting in the three aspects of legged locomotion: dynamics, physical interaction with environment, energy efficiency, and resonance-based dynamic locomotion. The main goal is to study two types of mechanical structure in their control in terms of energy efficiency. Quadrupedal robots, a good platform to study physical interaction with environment because of highly dynamics locomotion. Since galloping is a result of the action of inherently complex anatomy of animals or robotic structures, it's common to simplify analysis by using reduced order models and considering periodic motions of running. This spring-loaded inverted pendulum model featured is the most popular model for running analysis. This leap model can be implemented using a virtual and mechanical spring. The rough mechanics classification for galloping and walking robots legs depicted on slide. Fully octated open chain is one of the most common ways to implement a leg mechanism for a galloping robot. And under-octated open chain mechanism that utilize impedance control together these elastic elements to shift some same control to the mechanism structure. The under-octated closed chain mechanism that uses additional linkage with spring and deformable bodies to control the motion mechanically. That robots utilize the resonance-based motion of the physical elastic elements such as spring and deformable bodies. And fully octated closed chain mechanism without any elastic elements is commonly used for statically stable locomotion of walking robots since they are not able to perform resonance-based locomotion. The advantage of legs with an open kinematic chain is versatility to get any trajectory in working space, but execution of the trajectory falls entirely on the motors, which consumes a lot of energy. In mechanics with a closed kinematic chain, the number of possible paths is limited, but most of the path execution falls on the mechanics. This project focuses on a comparison of the fully octated open chain mechanism controlled with impedance techniques and under-octated closed chains mechanics control with position tracking algorithms in terms of energy efficiency. The open chain mechanism uses control system to implement physical interaction via a virtual spring damper system. The closed chain mechanism uses a physical spring to implement the same physical dynamics interaction with the ground. Much attention was paid when modeling motors. It's needed since they want to estimate electrical energy consumed for the simulation of the motors and other parameters for open chain and closed chain mechanism are considered the same. Such condition would create the correct model and set the thresholds for generated torque. The leg with the closed kinematic was discussed in our previous paper. The measure consumed energy of the robot during locomotion. The energy sampling method for embedded energy-aware actuators has been used. This method is needed to measuring how much energy actuators supply to the system. Dual method, it's possible to accurately estimate the energy supplied by the controller if the conditions are met. First, if the actuated force is constant during a single sampling period, and the second, that there is position sensor collected with the actuator. It's common to measure the cost of transport coefficients to study legged robots' energy efficiency. Cost of transport is a coefficient that quantifies the energy efficiency of the movement of animals, humans, or robot. The smallest cost of transport means the most energy efficient motion. Here you can see running sequence for the hopper with the open chain mechanism. This derivation of dynamics equations for impedance control. The impedance method of control is needed to handle an open chain robot's dynamic physical interaction with the ground. The control equation of the leg consider the inherent dynamics of a leg mechanism plus consider dynamics interaction. The under-octated robot with a closed chain has been created using the morphological computation. It means there was synthesis with consideration of the system's mechanical properties, mass distribution, compliance, and motion transformation via linkages. The idea to use little control effort to excite, stabilize, or augment natural dynamics of the robot's mechanical structure. Since the motion profile is already written inside the synthesis mechanism and the decide dynamics of the robot's motion inherently placed in mechanics, simple position tracking control algorithms can be used like PID generates. Here you can see graphs of energy consumption for two different mechanisms. To study various behavior of the open chain hopper, different coefficients for K and D have been tested for this equal. In some cases, the open chain hopper without spring behaviors unstable and losses functionality. However, a narrow range of values gives the level of cost of transport like 0.88. The best results that have been found are presented in this table. Another series of the simulation was performed to find the best possible options of cost of transport with embedded physical springs. Considering the table obtained values, it should be noted that using impedance control without springs, it's possible to achieve cost of transport equivalent 0.83 with future usage of springs. The coefficients can be reduced up to 0.45. The cost of transport has been improved in 1.8 times by adding the springs. Graph shows the fragments of the energy consumption at each instant moment. The graph shows only the central part of entire simulation science mechanism needs to reach the stable locomotion. It should be noted that the power consumption graph alone is not informative and should be read in conjunction with the cost of transport indicator. Here we can see that in the certain range of coefficients and K and D with embedded spring in the joints, it's possible to spend only energy with 3.5 joule every second. Analyzing the data of the closed chain mechanism is notable that the graphs slope approximately the same for each of simulation. This shows a change in the phase between the cranks has practically no effects on energy consumption, but only regularities the speed where we can see that it's possible to spend energy only 1 joule every second. In conclusion, we can say simulation have shown that integrating a real spring into the galloping robots like mechanism significant reduce transport cost in almost every case. A significant advantage of a mechanical spring can be noted due to its options continuous nature, which increase the system stability. The benefits of using of mechanical spring were quantitatively demonstrated by using an open kinematic chain mechanism as an example. The best indicator achieved in this work for an open kinematic chain cost of transport equivalent 0.45. It's important to note that the mechanism with a closed kinematic chain reaches cost of transport equivalent 0.12, which is 3.75 times less than for open chain mechanism. Despite the undoubted advantage of a closed chain in energy efficiency, the open chain remain versatile due to the possibility of reproducing different trajectories without changes in the hardware. Thank you for your attention.
Thank you a lot for your presentation. So I have a couple of questions. First of them related so about the masses of the open and closed loop chains, how they are comparable in this study.
Can you repeat, please?
The mass, how the if the masses in closed and open chains of the structure they are comparable. What is the ratio between the masses?
I'm sorry. Can you repeat again?
So I would like to know what is the mass of
Okay. Yeah. They are the same. The mass is the same. For first structure where open kinematic chain, and second structure where closed kinematic chain. They model this mass equivalent.
Okay. And okay, and another question I have about the spring realization, how they physically realized, and are there any issues or difficulties in terms of realization in open loop and closed loop chains?
Can you repeat?
So there are different ways how you can realize springs in the system. I would like to know how you assume to realize them in the open loop and closed loop chains you present, and if there are any difficulties related to the kinematics that affect on this.
Okay, we use the linear spring for closed kinematic chain and the torsion spring for open kinematic chain.
Mm-hmm. Is it it may be the factor of the difference or not?
Not this work equivalent.
Okay. Are there any other questions? So if no other questions, so I would like to thank again Roman for this nice presentation. So if we don't have the first speaker, the speaker of the first paper, so we will go to a short coffee break, and we will meet again in 15 minutes. So at 3:15. So we at half an hour. At 3:30. We will meet again. So just please connect 5 minutes in advance. I will check if everyone who should present the paper is here, and we will have another 5 nice presentations.
Can I start my report?
Yes. So you have from 10 to 12 minutes for presentation, and we'll have 5 minutes for questions. You may start.
Okay, thank you. So, good afternoon, and today I would like to present a report that deals with the control of a highly maneuverable mobile robot along curvilinear trajectories. First of all, let's start with the control object. First, in this work, a mobile robot with mechanism wheels will be considered as a control object. Mobile robots with these wheels have a distinctive feature. It is the ability to implement them in directional motion. Due to its ability, height maneuverability, the main area of the practical application of these types of robots is space such as warehouses or industrial premises. In the laboratory at the Kalashnikov Ижевsk State Technical University, various prototypes of mobile robots with mechanism wheels were developed. For example, education robots and prototype of a transport mobile robots. But previously developed methods of controlling robot were used mainly for mobile robots' motion along simple trajectories. Implementation of control along different complex trajectories can significantly expand the field of practical application of these robots. And further, the main highlights of the implemented work in this direction are considered. So, in order to describe the motion and implement the control, the mathematical model of the mobile problem with mechanism wheels was developed. The kinematic models assume that the roller of wheel does not slip at the contact point with the surface and describe the dependence of the angular velocities of wheels on the required velocity of the mobile robot. And in this work, we will determine the control using only the kinematic model. Consider the problem of controlling mobile robot along a trajectory specified in the parametric form. Let the function x, y, and phi describes coordinates of the mobile robot. These functions depend on the parameter s. The function s is intended to implement acceleration and deceleration processes and can be defined as a function sine squared. This substitution with the quadratic function provides zero initial speed condition for mobile robot. So we assume that the robot does not move initially. Thus, taking into account the considered substitution, the required control can be determined for typical trajectories, describing, for example, line, sine, circle, or various polynomials. But for motion along complex curvilinear trajectory, it is appropriate to describe required coordinates of a mobile robot in the form of piecewise functions, for example, using Bezier curves of the third order. This choice is motivated by the fact that curves of these types are usually used to describe curved line in the vectors graphics editors. The orientation of a robot will be taken to be constant, so phi is equal to 0. It should be noted that the mobile robot, when mobile robot moves along complex trajectories, it may be necessary to stop the robot completely at the points of the trajectory where there are sharp changes in the direction of motion. In this case, it is necessary to split complex trajectory into several segments with uninterrupted motion. And let's consider on the concrete example the control algorithm for determination of trajectory segments. The input data for computation are trajectory creating using the Bezier curves tools in the vector editor. Coordinates of the curves reference points are set in the SVG file. To determine the breakpoints where the robot will stop, it is necessary to compare the final and initial velocity vectors. Based on this comparison, a conclusion is drawn about presence discontinuity point. So X segments of the trajectory are determined where the motion will be continuous, and calculated time of motion of each segment, we form the piecewise function of S for the whole trajectory. And if we find the derivatives of coordinates function of the mobile robot, which are set in the parametric forms using Bezier curves, and the function of the parameter S, we can determine the control in the form of the angular velocities of wheels using the kinematic model. But to control the robot directly, it is necessary to transform these dependencies into an array of numbers with some discreteness. The generated array is transmitted to the control system of the mobile robot via serial data transfer interface. When this transfer is completed, using the prepared command, the robot starts moving along the trajectory, performing the required angular velocities of wheels. So the experiment was carried out to determine the efficiency of the proposed control method under real conditions. During the experiment, a directional mobile robot moved along a given curvilinear trajectory. Also, during the experiment, the real trajectory of the mobile robot was obtained. Okay. And graph of the real and theoretical trajectories are shown on the slide. Based on this data, the absolute position error was defined, which is about 20 millimeters. In conclusion, I will say that at this moment, the motion of an omnidirectional mobile robot along trajectories is implemented. Experimental investigation confirms the efficiency of the proposed method. The experimental data show a deviation of the real and theoretical trajectories. The main reason for this trajectory deviation is a slippage of the wheels rollers, which occurs when the robot fast changes its direction of motion. And the third future work will be focused on the optimizing calculation and compensation of position feedback control. That's all. Thank you for your attention.
Okay. Thank you a lot for your presentation. So if someone have questions, please type them in chat and I will post to the speaker. So while we wait for the questions, I will post some from my side. So first of them is, have you compared the trajectory planning that I implemented in commercially available mobile platform with the developed one? And what is the efficiency compared to them?
I don't understand about what comparison do you mean?
With the commercially available mobile platform, for example, with the KUKA platform, with the Amron mobile platform, with some others.
This platform can moves along maybe даже similar trajectories, for example, sine circle, but we can compare it experimentally. We can maybe do an analytical comparison.
Okay. So another question I have, so you mentioned in the last slide that you are going to work on the position error compensation. What source of inaccuracy you're expecting to have, and with which one you are going to work?
Going to use some local feedback system of feedback control, for example, with some beacons or cameras to use in this control.
No, that's the way how you're going to implement. But what is the source of inaccuracy you want to compensate? So right now, what is the source of these errors?
Now we have accuracy about 20 millimeters. Yes.
Okay. Yeah.
And we want to compensate about, for example, 1 millimeter.
Okay. Thank you. Are there any other questions from the audience? So if no, I propose to move to the next speaker. So next work will be presented by Yuri Karavayev from the Ijevsk State University. He will talk about stabilization of a spherical robot rolling on an oscillating Dorian surface. So please share your screen. Okay, you have 10-12 minutes for presentation and 3-5 minutes for questions.
Okay, can you hear me and can you see my screen?
Yes, we can hear you and we can see your screen.
Okay, let me start. So, dear colleagues, I'm glad to present the results of investigations of my team working in Ijevsk in 2 universities, in Kalashnikov State Technical University and Udmurt State University. My talk is devoted to investigation of the dynamics of spherical robot rolling on vibrating surface. First of all, I couldn't say about several designs on prototypes investigated and fabricated in our laboratory. On this slide, you can see 4 different constructions that implement different principles of motions. The first robot is spherical robot with 3 degree of freedom pendulum inside. The second one realized the model of chip-legging sphere with rotors inside, and for this model, the center of the center of the mass is located in the geometrical center of the sphere. The third one is the spherical robot with internal omni-wheeled vehicle. Each of these designs has its own features and disadvantages, but now we try to combine different designs to obtain best performance. That's why we designed the fourth prototype, the last one. You can see this from the right side. And this prototype combines the propulsion due to the changing the position of the center of mass and the changing the internal kinetic moment. Such combinations allows to implement different strategies of control that can help to reduce the friction, for example, or stabilize the motion of the robot. Recent works in dynamics of mechanical system demonstrate interesting results in case of periodically changing of their inertial or mass parameters, or in case of periodical control action or periodical interaction with other objects. The examples of such problems are, for example, constant accelerations of the Chapligin slides and Chapligin top in case of small periodic control actions, or due to the periodic change in the mass distribution. Another example, the acceleration of the Chapligin top with the help of an internal rotor, or behavior of Celtic stone line convibrating platform, the dynamics of rigid bodies with a vibrating suspension. For example, Lagrange tops, Kapitsa pendulum, well known. These examples motivate us to consider the motion of spherical robot on vibrating surface and investigate the motion by periodical control actions. Special for this, to solve this problem, we designed two prototypes of spherical robot of combined type. The robot on the left side sets in motion by a wheeled vehicle with rotor installed on it. The vehicle moves along a rim which connect two semispheres, and this vehicle provides the changing of the center mass position. The rotation of the rotor so the rotation of the robot arises when the rotor rotates. This robot has diameter 30 centimeter, and it was designed to implement periodical control action. The robot on the right side is smaller, only 10 centimeter in diameter. That's why it's best better for investigation of the dynamic in case of on vibrating or moving underlying surface. This robot sets in motion by this robot sets in motion due to changing the position of the center of mass by 1 degree of freedom pendulum installed in the spherical shell, and the rotor installed on this pendulum, and it provides the spinning motion of the spherical shell. The theoretical investigations, for theoretical investigations and development and control algorithm for both designs, the scheme of both designs are presented on this slide. And we described this, both designs as schematic model with spherical shell, which internal Lagrange pendulum. In case of motionless underlying surface, the kinematic of such system described with simple equations. And you can see this kinematic in this slide. the absence of sliding of spherical shell relative to the underlying surface described with non-holonomic constraint, and vector R here defines the position of the geometrical center of the spherical robot. It's our general approach. We investigate our mechanical system in form of D'Alembert-Lagrange equations. You can see on this slide the general form of such equation, and two kinetic moments here, k theta and k phi, are used for provide control action to pendulum and to rotor responding. So after reduction, we can obtain the system of equations that can use for design of control action, even in case of periodically control action, like periodical functions. You can see the reduced system on this slide, but now we consider another case when the spherical robot moves on moving surface. Just for example, we consider the periodically rotating underlying surface and introduce the internal kinetic moment in general form. It means kinetic moment has three components for evaluation for its influence on the dynamic of motion. In this case, the non-holonomic constraint defines by this equation the reduced system taken from the present. This is the reduced system for a new system, and in case of rotating base, in case it oscillates with periodical angular velocity with constant amplitude, the figure here show the trajectories of spherical robot by different values of kinetic moment. It's interesting that if we have no zero internal kinetic moment, we can stabilize the motion of the robot. And here is no kinetic moment, internal kinetic moment. This on this picture trajectory corresponds to the situation when kinetic moment has only one component and constant component. And when we will periodically change the only one component of kinetic moment, we obtain different trajectory of motion of spherical robot. This trajectory it's more stable, and the direction of motion in the same like we plan to do. And in on this third picture, the frequency of oscillation of the robot corresponds to oscillation of the base. So that's why it's important to know the parameters of underlying surface motion. To solve this problem, we introduce in the control system the feedback controller based on theoretical work of Ivanova, Kilin, Pivovarova, and taking into account the technical limitation of the current of DC motor and another electromechanical constants, we design the feedback, and the sham of this feedback controller you can see below. The parameters of vibrations we obtain using MEMS gyroscope installed in the spherical robot. So we compare the theoretical motion or model motion of the robot with sensors data, and then we can calculate the parameters of vibrating underlying surface. Unfortunately, due to the coronavirus limitation, we didn't try to any experiments with vibrating base, because we plan to do it in cooperation with our colleagues from Poland, from University of Łódź. They have built a special vibrating table and prepared motion capture system for evaluation the position and orientation of spherical robot. And I hope we will do it in next year. But we have tested the feedback controller for stabilization of motion of spherical robot when the surface is not flat, or when the spherical robot overcomes small objects. The example of such obstacle you can see on this slide. And two trajectories correspond to the motions. The solid line corresponds to the motion with this controller, and the dotted line corresponds to motion without a feedback. The pictures below demonstrate the same experiment, but there are presented components of units vectors that show the change in the orientation of the spherical robot by overcoming the obstacle. So the first plot is the component relative vertical axis, unit vector relative vertical axis, and the alpha vector shows the deviation from the direction of horizontal x-axis. So and so this picture demonstrates how works the controller and how it influences to the motion in such cases. When the robot overcomes the obstacle, he starts to oscillate, and then controller and feedback system obtain such oscillation and recalculate the control action for stabilization of this robot. So as a conclusion, I know that we stabilize the motion spherical robot of combined type using small oscillation of the rotor. We have designed a feedback for this under actuated system and have tested it by overcoming obstacles. And our future plans are in experimental investigations using vibrating table, real experiments, and also we plan to evaluate the influence of friction forces. Thank you for your attention, and you're welcome for any questions. I'm sorry, Alexander, I didn't hear you. Maybe you need to switch your.
Okay. Thank you for your nice presentation. Sorry, I muted the mic. While we're waiting for the questions, I will ask from my side. So I wonder how perfect shape is important for spherical robot, how its effect on the motion accuracy and motion capabilities of such a robot.
It's important, of course, it's important. You're right, but you know, in theoretical investigation, and when we want to just compare theoretical investigation and experiments, it's really important, because the friction forces and the quality of surface and the flatness of the surface, it's really important. in such experiments. But if we plan to build such robots, for example, just for monitoring task or observations of such places, it's enough to control of such robots, and don't take a lot of attention for the precision of such robots. Or we can, what we do now exactly, we try to plan and develop some feedback system for such system, for spherical robot. And then we can reduce this negative influence of quality of surface on the motion.
Okay, thank you, Yuri. In fact, I just lost that we are out of the time already. So let's move to the next presentation. So the next presentation will be given by Kirill Yefremov from the same group, and he will talk about theoretical and experimental investigation of the controlled motion of the roller racer. So please use your time. So you have 10 to 12 minutes for presentation, and we'll have 15 minutes for questions.
Oh, thank you, Alexander. Hello, everyone. Let me introduce myself. Today, I would like you present our research, which called theoretical and experimental investigations of a controlled motion of a roller racer. The roller racer is a system which consists of two platforms connected to each other by means of a cylindrical joint. The platforms can rotate in a horizontal plane relative to each other. Each platform has a rigidly attached wheel pair consisting of two wheels lying on the same axis. The propulsion of a roller racer is possible due to periodic oscillation of the platform relative to each other. In this slide, we can see a kinematic scheme of a roller racer. Mathematical model. We assume that the roller racer has no slipping at the point of contact of the wheel with the plane. Mathematical model includes kinematic parameters and dynamic parameters of roller racer. Kinematic and dynamic, which it means that we observe geometric, we include geometric parameters, mass, half platform, and every half, each half platform, and moment of inertia. Control function. For motion of roller racer, we need to use periodic control law. And for our research, we use modified sinus function. The function allows us to change the period and period of control, the general deviation of the angle, which designated as phi 0. And if we increase parameter n, we can stick at the top and the bottom on the function. This is a 3D model. Theoretical studies have shown the dependence of speed on the mass and the moment of inertia of the platforms. If we increase the moment of inertia, we can increase the speed of motion. This is a 3D model, first prototype of roller racer. Long rigid body attached at the front of the first platform give for us a big moment of inertia, which allows him to move. And this is second prototype because first prototype have a lot of moving parts, and we rebuild the prototype, and our second prototype has only one rotation joint. This for high accuracy. This is a video which present how roller racer move. For increased moment of inertia, we can add metal mass for each side. This metal mass presented like a metal pillow with 70 gram each metal mass. And in this slide, in this slide we can see the theoretical dependence of speed on the coefficient n and amplitude, which designated as alpha. And in this table, we can see some parameters of our model. Experimental prototype is platform, first platform, second platform, mass of first platform dot 71 kilogram, mass second platform is dot 33 kilogram, and other parameters. And in this graphic, we can see that if we increase parameter n, we can increase speed of our prototype. K parameter is speed of prototype. And this theoretical and experimental trajectories. The prototype was placed into a flat even surface to record the trajectory and the turning angles on the frame. Light reflected markers for the Viken motion capture system were placed on the first and second platforms. We can see that theoretical dashed line trajectories and experimental solid line trajectories. And we can see as we can see from trajectory graphics, propulsion of robot increase with increased amplitude of corn between the platform. Average velocity from top graphics consist around 35 centimeters per second, but average speed for bottom graphic consists around 13 centimeters per meter. This is graphic deviates only for amplitude, and if we increase amplitude, we can increase speed, and it's approved theoretical and experimental investigation. And this is theoretical and experimental trajectories for n equals 1, but this is trajectories for n equals 5. This is trajectories n equals 1. If if we decrease n parameters, we decrease slipping at the top and bottom function. Our speed decrease too. For this experiment, average speed consists 7 centimeters per meter. And the deviation of experimental trajectories from simulated ones stem from errors made in manufacturing and assembling the mobile robot, backslash at the joint, and the possible slipping of wheels. And thank you for attention.
Thank you for your presentation. Are there any questions from the audience? So no, no one is asking. So, what is the what was the main source of inaccuracy in the experimental setup you used? And are there any ways how to reduce it?
Accuracy for what? Accuracy for experiment? Accuracy for
yes, for position accuracy for experiment. Kirill, we cannot hear you. Kirill? We lost Kirill. Okay, so Kirill disconnected. So let's move forward in this case and go to the next presentation. Next presentation will be given by Mikhail Astanin from Innopolis University. He will present a work dealing with the stiffness analysis of the triptitron parallel manipulator. So please use your 10-12 minutes for presentation, and we'll have questions later on.
Okay. Firstly, do you hear me?
Yes, we can hear you.
Okay. Wait a few. Okay, do you see my presentation?
Yes, we can see your presentation.
Okay, thank you. Hello, everyone. My name is Mikhail Astanin. I'm from the Center for Technologies in Robotics and Mechatronics in Innopolis University. And today I want to present the work, stiffness analysis of the triptitron parallel manipulator. Let's start. The goal of our research is the develop of the stiffness model of the triptitron robot and compare result of the stiffness modeling from the different methodology. For achieve that goal, we set up a few tasks. Firstly, we need to develop the kinematic model of the robot. After that, we should use the virtual joint modeling method for the robot stiffness modeling. The third one, we should use the matrix structure analysis, robot stiffness modeling, and compare experimental results from the both technologies, virtual joint modeling and matrix structure analysis that we will use for the stiffness model. Firstly, what is the triptitron robot? In that picture, you can see the example of the triptitron robot that was provided in one work. The authors analyzed the dynamic of that robot. How you can see the simple robot that consists is a parallel robot. Each leg of that robot consists of the translation action joint, and free rotation joint connected by the links. By controlling the active joint, translation joint, we can set up the position of the end effector of our platform. The platform don't change the orientation. The orientation is the stable. Okay, let's go to the kinematic model of the robot. How you can see on the right side, we have the one more. We have the translation joint in each link. We have the simple double R robot for each link, which have the passive joint in the beginning, in the middle, and in the end of the link. For our formula, D is our controllable variable that we defined from our action joint, and Q is the vectors of the variables of the passive joints. Of course, we should divide not only for kinematics, we should divide also the inverse kinematic for find the exact position of the each joint for the given position of our platform of our end effector. The translation position is easily divided directly from the position of the end effector. dx is equal to the x, dy is equal to the y, and dz is equal to the z. And the position of the passive joints we can easily define from the equations like for the planar double R robot. And let's go to the stiffness. We define our stiffness of each links as the cylindrical beams. We approximate it, and each kinetic and stiffness matrices K for each cylindrical beams consist of the 4 6x6 matrices that you can see on the screen, where K11 is the stiffness matrices of the left side of the beam. If we apply force for the left side, for example, K12 is our stiffness if we apply of the left side, if we apply force to the right side, and K2 is stiffness of the right side of the beam if we apply force to the right side. Here we define the stiffness of each flexible link. Let's go to the first methodology that we use for the stiffness modeling, that calls virtual joint modeling. The idea of that method that we represent each part of our legs, each part of our robot to the rigid part and flexible springs. For example, we have the rigid base. After that, we have the action joint, and after it, we set up the one-dimensional degree spring, and we define the theta 1 that describes the deflection in that spring. After that, we have the passive joint around Z, for example, for one of the link. Finally, we have the rigid link, and after the rigid link, we have the flexible. We have the spring, 6 degree of freedom spring that represent each deflection of our flexible link. Finally, after that, we have also the passive joint, second passive joint. We have the rigid link. We have one more 6 degree of freedom spring, and in the end of each leg, we have one more passive joint, and we have connection to our platform, to our tool. As a result, we have matrices K theta, which has dimensions 13 by 13, which represent the stiffness of each springs. By that formulas, we can calculate the final Cartesian stiffness matrices of each link of the robot. Totally, we have the 3 links, therefore we have the 3 KC, and we assume that each legs in our platform connected in one point. It means that that platform is equal to the 0 and each link's connected to the one point. Therefore, we can easily sum our stiffness matrices KCI, and finally we found total stiffness matrices of the robot. As a result, from the virtual joint modeling, we have that 6x6 matrices for our robot. Let's go to the second methodology. It's matrices structural analysis. In that method, we also divide our links, each link to the separate connection for few nodes. First node is a rigid-based. Second node located after our joint, our active joint. We have the passive joints, we have the flexible links, and we have one more flexible joints. And we assume that our first active joint and our first passive joint connected via a rigid link. It's very important. And the same thing we do near the end effector. They assume that our last passive joints connected to the platform via rigid link. And connection 4, 5, 6, 7 is our flexible links. And our actuation joint also have one elasticity in degree of freedom of the joint. Okay. According to the matrix structure analysis, for each connection, we have some matrices equation, which goes from the hook laws. For rigid base, we use that equation. For our flexible links, they use that equation. The K11, K12, K21, K22 stiffness matrices goes from the stiffness matrices of the each links. For the rigid connection, near the links, link 8, and near the connection between node 2 and 3, they use that formula where D will equal to the identical matrices. Why? Because we assume that is like a 0 length. As you see before, we just add virtual rigid link. It means that that length will equal to the 0. Therefore, D matrices there will equal to the identical matrices. And similar will be there. Of course, we have the matrices for the elastic joint 1 between node 1 and 2, where lambda r define the rigid connection in our joints, and lambda e is the vector which define the elastic joints, elastic degree of freedom in our joint. Of course, we have the passive joint, and we have another formula for the passive joints that you can see here, where similar as above, lambda r define the rigid connection in our joint, and lambda p define the passive connection of our joint in our joint. Of course, we also have some external torques, external connection. And finally, we should aggregate whole that matrix equation to the one big matrices equation. In that, you can see the dimensions of that equation. Our aggregated range vector will be equal to the 54 variables. Our delta t aggregated vector will be equal to the 48 variables. And we have the 6 delta E, the free translation and free rotation delta. Range we equal to the 6x1 vector because we have free force and free torques. And finally, for calculation the stiffness matrices of the link, of the one link, we use that combinations, that equations that define, that goes from our matrix equation that we get from the collecting whole previous equation. As a result, we have the Kc for each leg, and we apply the same assumption that our E point, our platform is 0, and E point is equal to the each link. Therefore, we can easily apply that formula, that one. Finally, as in previous case, with virtual joint modeling, we have 6x6 Cartesian stiffness matrices for whole robot. After implementing that two approaches, we try to build the deflection map of each robot. We tried a few experiments. For some configuration in workspace, firstly, we applied the force along the x-axis. After that, we applied the force along the y-axis. And in the third picture, we provide the force along the z-axis. How you can see the maximum deflection located in the line which opposite to the controllable line of that robot along that axis. For example, that in that line, we have our translation joints that control the x position. We apply the force along the x-axis, and the maximum deflection for that forces we see on the line which are opposite for the workspace of our robot from our controllable line. We the size of the deflection, it's approximately 1.5 millimeters. So the 1,000 force, 1,000 newtons force for some numbers, Kc for our joints and for our links. Okay, we also try to apply, we also try to find the maximum deflections, maximum available deflection in some points. We apply the same force, but we apply it in any direction, and we try to pick the maximum deflection of from that experiments. That map, deflection map, show you the maximum deflection for the robot robot workspace. How you can see it located in that point. Yeah, because that point is opposite to the points that intersect two control lines. Yeah. The maximum deflection is equal to the approximately 1.6 millimeters. The last goal of our research was to compare results between two methods, matrix structure analysis and virtual joint modeling methods. We do it. Firstly, we compare the computational efficient of our methods. For our implementation, MSA give us the faster results in 20 times than VGM approach. And we try to compare the differences between the result, the differences between some deflections in the points for the same force for different model from the VGM approach and from the MSA approach. And how you can see the results show us that we have the same result. We have the same KC matrices from the both methods, and the error power is minus 15. It means that less than computational accuracy of our calculation. We use Python, and Python originally gives 10 in minus 12 computational accuracy. We have less than, that means that our methods gives us equal results. Conclusion, we done a kinematic model of the trip-tron manipulator. We provide the VJM approach, virtual joint modeling, MSA approach, and compare them. The results gives us that VJM slowly than multi-structure analysis, but the two methods also give us the similar results. In future work, we plan to develop some method that gives us intuition how we need to change the model of our robots. For example, how we need to change the flexibility of the joints to achieve some condition for the whole robot. Also, we will try to minimize the computational effort of the virtual joint method because it gives us much slower than MSA. And finally, we will try to investigate some methods, some stiffness error for stiffness error compensation. Thank you for your attention. Questions?
Thank you, Mikhail. So we have one question from the chat. Deflection of 1.5 millimeters is very less for 1,000 newtons. What may be the reason? Is it a practical result? Any ideas, prediction about experimental results?
Do we have such results because we have very strong beams? They assume that they are we have, for example, that data we set up very strong approximation of our links. Therefore, we have that less deflection.
Okay. And I have another question related to the approximation you use here. So you use cylindrical beams to represent the links. However, the connections of joints, it's not, you cannot approximate with the cylindrical links. How this will affect the final result if you want to compare this with the real prototype?
For the real, originally we have some CAD model for the real prototypes, and we can take the stiffness matrices for each link from the CAD model, from our CAD system, and we can apply it to the our code as the stiffness matrices of the link, and we can see the result. Did you answer for your question?
No, the question was how accurate the result, the approximation you use now.
I think now it's not very accurate approximation for the if we compare for the real robot, but we don't have the real robot, and therefore we have the possibility to use some approximation.
Thank you. So thank again, Mikhail. So it's time to move to the last presentation of our session. So it will be given by Ramil Kusainov, who represents Innopolis University, and he will talk about ROS-based swing-up control and the stabilization of the Pendo bot using virtual holonomic constraints. So please use your 10-12 minutes for presentation, and we'll have 3-5 minutes for questions.
Okay. Can you hear me first of all?
Yes, we can hear.
And can you see my
yes,
presentation?
We can see.
Okay, so the topic of my presentation is actually the control of the underactuated system and the Pendobot as an example of such system. So underactuated systems are common in robotics, and there are many systems that have such property. For example, Bipedal robots in some phases of the motion are considered as an under-actuation system, or aerial vehicles, they are considered as under-actuated systems. So all the systems where the the number of control inputs are less than the number of degrees of freedom are called under-actuated systems. So in our lab, we've constructed an example of such system, which is a pentobot, and it's showed on this figure. So the pentobot is actually a two-link robot, and the first link, the shoulder link, is controlled by in our case, by brushless direct current motor. So we directly can apply the torque that we want. And the second link is passive. So in both, the second joint is passive. So in both joints are, we can measure the angle of the joints using the encoders, and we can estimate the angular velocity using numerical differentiation algorithms. So this is on the slide, you can see the model of the pentobot with the inertia matrices, the C matrix with Coriolis and centripetal forces, and the gravity vector. So here the U is a control input, and in our case it's the B matrix. The B vector is 1, 0, which means that we have a torque input port torque in the first joint, and the second joint is passive. So the goal of our work was to swing up, to make a swing up of the pentobot, which means that initially pentobot, this one is hanging down in its stable equilibrium position, and then we are trying to make it swing up such that the first angle, the first link is directed downward, but the second link is directed upward. So we have to came to the non-stable position and stabilize it. So to do this, to perform this task, we used the virtual holonomic constraints framework, which can be divided into two parts. First one is trajectory planning, and the second one, the control of this along this trajectory. So the virtual holonomic constraints concept based on the idea that during the desired motion, along the desired motion, the following equalities should be satisfied. So there should be a connection between 2 degrees of freedom. In our case, the theta is the elbow and the phi is the shoulder. So we are searching for the trajectories where there is a connection between these 2 degrees of freedom. In this case, if we substitute it to the previous model of the dynamics into dynamics equation, we can get the so-called alpha beta gamma equation. So it's for all mechanical systems, Lagrangian systems. It has the following form, and so in our case, the alpha beta and gamma, which are the functions of depending on S. So S is called the motion generator. In our case, it is the elbow joint. The values are given on the slide. So solving this ordinary differential equation of the second degree, we can get the nominal trajectory, and by choosing the phi 0 and k, we can change this desired motion. So in our case, we used the two nominal trajectory. First one to start with, we are using the k. So the connection between two angles like 0.1, which means that the first angle is oscillating 10 times smaller amplitude oscillation of the oscillations of the amplitude 10 times smaller than the second elbow joint. Okay, and then we step by step we switch from one trajectory to another by increasing increase our amplitude of the oscillations. And then for this is called the propeller motion with k is equal to 0, which means that we have the first shoulder joint fixed and the elbow joint is rotating like a propeller. So when the propeller motion, so when we have the propeller motion and the second joint comes to the non-stable equilibrium point, we switch to the LQI, which is derived for a linear system. So we linearize it, the pentobot around the non-stable equilibrium point, and use the LQR stabilization. So this is about the trajectory planning. So the control is based on the framework which was derived by Professor Anton Schramm and his team. So it's about the transversal linearization. So we introduce into system the so-called transversal coordinates. In our case, it is like a wise deviation from the nominal trajectory. So if we look at the nominal trajectory in the phase space, actually y dot, and some values called the integral of the motion are the three variables in our case which show the distance to the nominal trajectory. So by introducing this variable, we can rewrite our dynamics in vicinity of the nominal motion in the following form. So it's like it's performed using the partial feedback linearization. So here we have this alpha beta gamma equation, which is 0 on the nominal trajectory and non-zero in the vicinity of the nominal trajectory. And U is actually our input torque. And here's the connection between V, which is also 0 on the nominal trajectory, and the input torque. So this is like the same case as a partial feedback linearization. And by linearizing this system in vicinity of the motion, we get the LTV, linear time variance system, with the following matrices A and B. So having these matrices, we can solve this, try to design the controller, which will, in the form of V is equal to K times epsilon, which will stabilize this, which will contract this linear time variance system. Okay, and this is done by solving we use the external package for solving the Riccati differential equation, which gives us the matrix K, and then we substitute it into, we use the K matrix to calculate the V. So as I said, we have several nominal trajectories by so that the amplitude of the oscillations are increasing. Then we switch to propeller motion, and then we in the upper position we are switching to the LQR, which stabilizes this desired position so that the swing up ends. So these are the results. We actually, the goal of the paper was to compare the numerical results with the experimental setup. So when the numerical results were derived for both in MATLAB and in Gazebo. So why we did it first in Gazebo? Because in Gazebo we could simulate the real-time issues, so that for example, the transversal coordinates are calculated real time, and so we need there is an accuracy loss in calculation of some values. So it has an effect on the final result. So we can see, for example, the transversal coordinates, which, as I said, is the distance from the nominal trajectory. They are oscillating, okay, and the amplitude of oscillation in Gazebo is much higher than in MATLAB. In MATLAB, we can do it like not real time. We can use as high accuracy as we want. Okay, and the same for integral. The amplitude of the oscillations in Gazebo are much higher than in MATLAB. So when we come to the real experiments, we have even worse. The results are even worse, especially for again integral. So on the right side figure, you can see that we have the amplitude is almost like 15 or 20, and it is higher than the numerical experiments. But still, we could succeed to make a swing up. Okay, so we can switch from one trajectory to another, and then switch to propeller motion, and then stabilize it in the upper position. So what are conclusions that we've seen from our results? So the approach showed satisfactory results in both simulation experiments, but we noticed that the trivial layer cannot completely nullify the transverse coordinates in the orbital stabilization problem. And this is the problem if we want to stabilize, if we want, for example, to have a limit cycle around the non-stable point. So in that case, these oscillations of the transversal coordinates, they are critical, and the system becomes unstable and falls down. So this will be our next step to make controller more robust to some uncertainties and in the system and accuracies in the calculations of the transversal coordinates. And also we will notice the importance of choosing the nominal trajectory in terms of dimensions of traction and the moment of choosing switching between these nominal trajectories. So in other words, when we start from the rest position in a lower equilibrium point, the different nominal trajectories and the different parameters of the controller give different results in terms of whether it converges to the nominal trajectory or not. And sometimes the convergence was not, there was a divergence. So when we related to the domains of attraction and again, the tuning of the controller. So this is an important issue if we want to, for example, have a goal of make a swing up in the fastest way. And this is the main conclusions, and thank you for your attention.
Thank you, Ramil. So we have a question. So how do you define the equation that define a relation between theta and phi?
Okay, good question. This is actually like it depends on what you want. Okay, so we choose the simple case where we have a linear relation, but it is okay for in our case. If you want some, as I said, if you want some, if you set the goal as to find some optimal trajectory, okay, and then in that case, this could be more difficult, more complex functions like polynomials. For example, phi can be as a polynomial of the n degree of the theta, and you use the numerical optimization to find this function. Okay, but in our case, we didn't have such goal, so we choose the simplest case. Okay, and the calculations are simpler, much simpler for this case. But in other words, for example, in bipedal locomotion, we did the other choice. We found this virtual holonomic constraint function to have some optimality. So that's it.
Thank you. I have another question. So can you highlight the advantages of transversal coordinates?
The advantages is actually, if we speak about the general or this for this swing up problem.
I would ask to say in general and for this particular problem.
In general, of course, it has some benefits because first of all, it is like a universal framework for stabilizing a limit cycle. So if you have some underactuated mechanical system and you have some periodic motions, so this is like a universal framework to stabilize such motions, periodic motions. And for swing up, actually, it's a good question because we haven't compared it with other approaches, but still we just wanted to test it. Okay, so to test this framework on this problem and to see the results and to compare the results of, I mean, the simulation and the experimental setup. But yes, there are. I cannot point out the benefits for particular problem of this transversal coordinates framework.
Okay. And I have another question. Which type of feedback are you used in this experimental setup?
So the feedback, as I said, is this like a V function. Okay, so we at each time instance we calculate our transversal coordinates. So this is the epsilon vector. Okay, and we have the K matrix, which is the solution of the Riccati equation, and we have the V in form of K times this epsilon. And after that, we substitute this V into this partial feedback formula. So here we have V, and we have N and R functions, such that we have the full torque. Okay, the full torque which we apply to the first joint, the shoulder joint. So this is how it works.
Thank you. If you don't have any other questions, so I would like to thank Ramil again. So I would like to thank everyone who participated in the conference today, and we will continue tomorrow in the morning, in the 10 of the morning. So we will have I would say the greatest keynote. So we'll have you'll have an opportunity to listen for the best in the research in the subject researchers to give a state of the art on their area, and to ask them the most tricky questions you have to get the best answers you can have on these topics. Thank you all for participation, and good luck for everyone.